Stars, the celestial engines of the cosmos, undergo a spectacular life cycle that spans millions to billions of years. Their journey begins in the cold, dense regions of interstellar space, and their fiery demise often leaves behind some of the universe's most enigmatic remnants. Understanding the life and death of stars reveals the processes that shape galaxies, seed the cosmos with heavy elements, and drive the dynamic evolution of the universe. Stars are born within molecular clouds, vast regions of cold gas and dust that are scattered throughout galaxies. These clouds, often stretching across hundreds of light years, contain the raw material for star formation. Gravity begins the process, pulling clumps of gas together into dense regions known as protostellar cores. As these cores collapse, they heat up due to the conversion of gravitational energy into thermal energy. In the center of the collapsing cloud, a protostar forms, surrounded by a disk of gas and dust. This disk, known as a protoplanetary disk, is the birthplace of planets, moons, and other celestial bodies. The journey from a protostar to a full-fledged star is marked by a dramatic event, the ignition of nuclear fusion. When the core temperature reaches approximately 10 million Kelvin, hydrogen nuclei begin to fuse into helium, releasing immense amounts of energy. This marks the birth of a star, a delicate balance between the inward pull of gravity and the outward pressure of radiation and heat. Once nuclear fusion begins, the star enters the main sequence, the longest and most stable phase of its life. During this time, the star fuses hydrogen into helium in its core, producing the energy that radiates as light and heat. As the star ages and depletes its hydrogen fuel, its core contracts while its outer layers expand, transforming it into a red giant or supergiant, depending on its initial mass. For lower mass stars like our Sun, this expansion leads to a gentle shedding of outer layers, forming a planetary nebula that surrounds a dense core, which becomes a white dwarf. This faint, cooling remnant is the final stage for such stars, gradually fading over billions of years. For massive stars, the end is far more dramatic. As their cores collapse, they trigger supernova explosions, some of the most energetic events in the universe. These explosions scatter heavy elements into space, enriching the interstellar medium and paving the way for new star formation. The remnants of these explosions may form neutron stars, incredibly dense objects with intense magnetic fields, or even black holes, regions of space where gravity is so strong that not even light can escape. The death of a star is not the end of its contribution to the cosmos. The elements forged in its core and released during its final stages become the building blocks for new stars, planets, and even life. In this way, the life cycle of stars drives the ongoing evolution of the universe, connecting the past, present, and future in a cosmic cycle of creation and renewal. The evolution of galaxies, from cosmic clouds to grand structures. Galaxies are the grand architectural masterpieces of the universe, vast systems of stars, gas, dust, and dark matter that shape the cosmos and host the processes of stellar creation and destruction. These immense structures, ranging from humble dwarf galaxies to sprawling spiral and elliptical galaxies, are the result of billions of years of cosmic evolution. Their formation and transformation tell the story of the universe itself, from its chaotic beginnings to its ongoing expansion. The origins of galaxies can be traced back to the early universe, just a few 100,000 years after the Big Bang. During this epoch, known as recombination, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. This event left behind the cosmic microwave background, CMB, a faint glow that provides a snapshot of the universe at this formative stage. Tiny fluctuations in the density of matter, imprinted during the inflationary epoch, served as seeds for the formation of galaxies. These fluctuations allowed gravity to pull matter together, forming the first structures known as dark matter halos. Dark matter, the invisible scaffolding of the cosmos, played a critical role in this process. Although it does not emit or absorb light, dark matter exerts a gravitational influence that draws ordinary matter into dense regions. Over time, these regions grew, forming the first protogalaxies. These small, irregular systems were the ancestors of modern galaxies, housing the earliest stars, known as population II stars. These stars were massive, short-lived, and composed almost entirely of hydrogen and helium, as heavier elements had not yet been created. The The death of these early stars, in powerful supernova explosions, enriched the surrounding gas with heavier elements, known as metals in astrophysical terms. This enrichment enabled the formation of more complex structures, including second-generation stars, planetary systems, and eventually life. As these processes unfolded, galaxies began to grow and evolve through mergers and accretion. Small protogalaxies collided and coalesced, forming larger and more organized systems. This hierarchical growth, driven by gravity, shaped the diverse galaxy types we see today. The morphology of galaxies, whether spiral, elliptical, or irregular, is influenced by their history of interactions. Spiral galaxies, like the Milky Way, are characterized by rotating disks of stars and gas, with prominent arms that often host active star formation. These galaxies are thought to form through the gradual accretion of gas and minor mergers, which preserve their disk-like structure. Elliptical galaxies, on the other hand, are more spherical or elongated and lack the prominent features of spirals. They are typically the result of major mergers, where two or more galaxies collide and their stars are redistributed into a more random configuration. Irregular galaxies, with their chaotic shapes, often bear the scars of recent interactions or the gravitational influence of nearby neighbors. The evolution of galaxies is also shaped by the processes occurring within them. Star formation, driven by the cooling and condensation of gas, transforms galaxies over time. Massive stars, though short-lived, play a particularly influential role. Their intense radiation and stellar winds heat and disperse gas, while their explosive deaths as supernovae inject energy and heavy elements into the interstellar medium. These processes, collectively known as stellar feedback, regulate the rate of star formation and influence the structure of galaxies. Supermassive black holes, which reside at the centers of most galaxies, also play a pivotal role in galactic evolution. These black holes, millions to billions of times the mass of the Sun, grow by accreting matter from their surroundings. During periods of high activity, they power active galactic nuclei, AGN, and quasars, emitting enormous amounts of energy that can heat or expel gas from the galaxy. This feedback mechanism can quench star formation, transforming active, star-forming galaxies into quiescent systems. Galaxies are not isolated systems. They exist within larger structures called galaxy clusters and superclusters, interconnected by the cosmic web. The environment of a galaxy, whether it is part of a dense cluster or a more sparsely populated region, influences its evolution. In clusters, galaxies experience processes such as ram pressure stripping, where their gas is removed by interactions with a hot intracluster medium. This process can halt star formation and contribute to the transformation of spirals into ellipticals. The interplay of these internal and external factors creates the dynamic and ever-changing tapestry of the universe. Observations of distant galaxies allow astronomers to look back in time, revealing the stages of galactic evolution over billions of years. For example, deep-field images from the Hubble Space Telescope have captured light from galaxies as they appeared less than 1 billion years after the Big Bang, providing insights into their early formation and growth. In the future, galaxies will continue to evolve as the universe expands. Our own Milky Way is on a collision course with the Andromeda Galaxy, a spiral galaxy approximately 2.5 million light-years away. This cosmic encounter, expected to occur in about 4.5 billion years, will reshape both galaxies, likely merging them into a single, massive elliptical galaxy. Such events, though dramatic, are part of the ongoing life cycle of the cosmos, ensuring its perpetual transformation. Through the study of galaxies, we gain a deeper understanding of the universe's history and the processes that have shaped it. Galaxies are not just collections of stars and matter, they are dynamic systems that reflect the forces and interactions of the cosmos. Their evolution is a testament to the intricate and interconnected nature of the universe, a story written in light and gravity, spanning billions of years. Black holes, gateways to the extremes of physics. Black holes are among the most enigmatic and fascinating phenomena in the universe. These objects, where gravity is so intense that not even light can escape, represent the ultimate triumph of gravitational forces. They are more than just cosmic oddities, they are engines of transformation, shaping galaxies, influencing the flow of matter and energy, and pushing the boundaries of our understanding of physics. Black holes come in several varieties, each with unique origins and characteristics. Stellar mass black holes form from the collapse of massive stars at the end of their life cycle. These stars, having exhausted their nuclear fuel, undergo supernova explosions, leaving behind dense cores that collapse under their own gravity. If the remnant is massive enough, exceeding about 3 times the mass of the Sun, it becomes a black hole. At the centers of galaxies, however, lie supermassive black holes, which are millions to billions of times more massive than the Sun. The formation of these cosmic giants remains a mystery. They may grow from smaller black holes through mergers and accretion, or they might have formed directly from the collapse of massive gas clouds in the early universe. Their immense gravitational influence shapes the evolution of their host galaxies, anchoring their centers and often powering active galactic nuclei (AGN). Supermassive black holes are associated with some of the brightest objects in the universe, including quasars. Quasars are powered by matter falling into the accretion disks of black holes. As this material spirals inward, it is heated to extreme temperatures, emitting energy across the electromagnetic spectrum. These luminous beacons can outshine entire galaxies, making them visible across billions of light years. Intermediate mass black holes, with masses between stellar and supermassive black holes, have been elusive, but recent discoveries suggest they may exist in dense star clusters or the centers of dwarf galaxies. Their formation pathways are not well understood, and finding them could help bridge the gap between stellar mass and supermassive black holes. Theoretical physics suggests that primordial black holes, formed shortly after the Big Bang, could exist as well. These black holes, ranging from microscopic to planetary masses, might offer clues about the early universe and the nature of dark matter. If detected, they could provide a window into the conditions of the universe's first moments. The event horizon of a black hole, the boundary beyond which nothing can escape, is a defining feature. At this threshold, space and time are warped to their limits, creating an area of no return. The Event Horizon Telescope, EAT, made history in 2019 by capturing the first ever image of a black hole's shadow in the galaxy M87. This breakthrough confirmed theoretical predictions and provided a direct glimpse of the warped space-time near a black hole. Black holes are not merely regions of empty space, they are dynamic systems with profound effects on their surroundings. Their immense gravity pulls in nearby matter, forming accretion disks of gas and dust. The intense heating of this material, as it spirals inward, generates powerful jets of particles, which can extend thousands of light years into space. These jets influence galaxy formation and can even regulate star formation by injecting energy into the surrounding medium. The physics of black holes challenges our understanding of the universe. At their cores lies a singularity, a point of infinite density where the laws of physics as we know them break down. General relativity, which describes gravity on large scales, and quantum mechanics, which governs the behavior of particles on small scales, are incompatible in these extreme conditions. Understanding singularities requires a theory of quantum gravity, one of the greatest goals of modern physics. Recent research has also explored the possibility of black holes serving as gateways to other regions of space-time, or even other universes. Wormholes, hypothetical tunnels connecting different points in space-time, could theoretically form under certain conditions. While there is no evidence that wormholes exist, their study offers intriguing possibilities for understanding space-time and the universe's structure. Hawking radiation, a theoretical prediction by Stephen Hawking, suggests that black holes can slowly lose mass over time. This radiation arises from quantum effects near the event horizon, where particle-antiparticle pairs are created. One particle falls into the black hole, while the other escapes, effectively reducing the black hole's mass. Over immense timescales, this process could cause black holes to evaporate entirely, though this has yet to be observed directly. Black holes also play a pivotal role in the detection of gravitational waves, ripples in space-time, caused by the acceleration of massive objects. The first detection of gravitational waves in 2015 by the LIGO and Virgo observatories came from the merger of two stellar mass black holes. These observations have opened a new window into the universe, allowing scientists to study black holes and their interactions in unprecedented detail. The influence of black holes extends beyond their immediate surroundings. Supermassive black holes can regulate the growth of their host galaxies through feedback processes. By expelling gas and heating the interstellar medium, they can suppress star formation, shaping the galaxy's evolution over billions of years. Observations of distant galaxies and simulations of galaxy formation reveal the profound impact of these cosmic giants. The study of black holes continues to push the boundaries of science, combining observational astronomy, theoretical physics, and advanced technology. Future missions such as the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from black holes in even greater detail, while next-generation telescopes will explore their accretion disks and jets. Black holes remind us of the universe's extremes, from the immense scales of space-time to the smallest quantum effects. They are both destroyers and creators, transforming the matter and energy of the cosmos and challenging our understanding of reality itself. Through their study, we not only learn about the forces that shape the universe, but also confront the limits of human knowledge, venturing into the deepest mysteries of existence. The cosmic web, the universe's grand design. The universe is not a random scattering of galaxies and matter. Instead, it is organized into an intricate and vast structure known as the cosmic web. This web is a network of interconnected filaments composed of galaxies, gas, and dark matter, stretching across billions of light years. Between these filaments lie immense voids, vast expanses of nearly empty space. The cosmic web represents the large-scale structure of the universe, a result of billions of years of evolution driven by gravity and the mysterious forces of dark energy and dark matter. The formation of the cosmic web began shortly after the Big Bang, when the universe was a nearly uniform expanse of hydrogen, helium, and dark matter. Small quantum fluctuations, amplified by cosmic inflation, created regions of slightly higher density. Over time, gravity acted on these denser regions, pulling matter together and forming the seeds of the structures we observe today. Dark matter, which makes up about 27% of the universe's energy density, played a critical role in this process. Its gravitational influence drew ordinary matter into dense regions, forming the backbone of the cosmic web. As the universe expanded, these dense regions grew into filaments, the highways of the cosmic web, where galaxies and clusters are concentrated. The intersections of these filaments, known as nodes, are home to massive galaxy clusters containing thousands of galaxies bound together by gravity. Between the filaments lie vast voids, regions with few galaxies and low densities of matter. These voids are not entirely empty but contain traces of gas and dark matter, stretching across millions of light years. The cosmic web structure is best revealed through large-scale galaxy surveys and simulations. Observations, such as those from the Sloan Digital Sky Survey, SES, have mapped the positions of millions of galaxies, showing the intricate patterns of filaments and voids. Advanced simulations, like the Millennium Simulation and Illustris project, use supercomputers to model the evolution of the universe, reproducing the cosmic web's formation and revealing insights into the underlying physics. The role of dark matter in the cosmic web is particularly significant. While dark matter is invisible, its gravitational effects shape the distribution of galaxies and clusters. Observations of gravitational lensing, where the gravity of massive structures bends the light from distant galaxies, allow astronomers to map the distribution of dark matter, revealing its connection to the visible components of the web. The cosmic web is not static. It evolves over time as gravity pulls matter into denser regions and dark energy drives the accelerated expansion of the universe. In the early universe, matter was more evenly distributed, but as time progressed, the filaments and clusters grew more pronounced. This ongoing evolution provides clues about the forces shaping the cosmos, from the interplay of dark matter and dark energy to the effects of galaxy formation and feedback. Galaxies within the cosmic web are not isolated. Their environments influence their evolution. Filaments act as highways, channeling gas and galaxies toward clusters. This flow of material fuels star formation and the growth of supermassive black holes. In clusters, galaxies experience interactions, such as mergers and tidal stripping, which shape their morphology and star formation rates. The environment also plays a role in quenching star formation, as galaxies in dense regions lose their gas through interactions with the hot intracluster medium. Voids, despite their emptiness, are important laboratories for studying the universe. These regions provide a contrast to the dense environments of filaments and clusters, offering insights into how galaxies form and evolve in isolation. Voids are also sensitive to the effects of dark energy, making them valuable for testing theories about the universe's accelerated expansion. The study of the cosmic web extends beyond its structure to its role in the universe's overall evolution. The web is a framework for the distribution of galaxies, but it also influences the movement of gas and the formation of stars and planets. The interplay between filaments and voids drives the flow of material, shaping the observable universe on the largest scales. Recent discoveries have revealed additional layers of complexity within the cosmic web. Observations of the warm, hot intergalactic medium, WIM, a diffuse gas component of the web, suggest it contains a significant fraction of the universe's missing baryons. These baryons, composed of protons and neutrons, are thought to reside in the filaments, heated by the gravitational collapse of the web's structures. The cosmic web also offers a window into the past, as light from distant galaxies and quasars travels through its structures. By studying the absorption of light by the intervening gas, astronomers can trace the history of the web and its interactions with galaxies and black holes. These observations provide a record of the universe's evolution, from the formation of the first structures to the present day. The future of cosmic web research is bright, with upcoming telescopes and missions promising to reveal its intricacies in unprecedented detail. Instruments like the Vera C. Rubin Observatory and the Euclid Space Telescope will map the distribution of galaxies and dark matter, uncovering the hidden dynamics of the web. Advances in computational power will enable even more detailed simulations, bridging the gap between observation and theory. The cosmic web is a testament to the universe's complexity and interconnectedness. It is not merely a backdrop for celestial objects, but an active and evolving structure that shapes the cosmos. By studying the cosmic web, we gain a deeper understanding of the forces that govern the universe, from the formation of galaxies to the nature of dark matter and dark energy. The web is the universe's grand design, a reflection of its origins, its present state, and its future potential. Exoplanets, the search for other worlds. Among the most exciting and transformative fields in modern astronomy is the study of exoplanets, planets that orbit stars outside our solar system. In just a few decades, astronomers have discovered thousands of these distant worlds, revealing a diverse and astonishing array of planetary systems. The search for exoplanets has reshaped our understanding of planetary formation and evolution, and brought us closer to answering one of humanity's most profound questions: are we alone in the universe? The first confirmed detection of an exoplanet came in 1992, when astronomers Alexander Wolszczan and Dale Frail discovered planets orbiting a pulsar, a type of rapidly spinning neutron star known as PROS B12 5712. These planets, exposed to intense radiation from their host, were unlike anything in our solar system. Just 3 years later, the discovery of 51 Pegasi b, a Jupiter-sized planet orbiting a Sun-like star, confirmed the existence of exoplanets around main sequence stars, sparking a revolution in the field. The techniques used to detect exoplanets are as varied as the planets themselves. The transit method, the most successful detection technique, identifies planets by observing the slight dimming of a star's light when a planet passes in front of it. Space telescopes like Kepler and TESS, transiting exoplanet survey satellite, have used this method to discover thousands of exoplanets, including Earth-sized planets in the habitable zones of their stars. Another widely used technique is the radial velocity method, which measures the tiny wobble in a star's motion caused by the gravitational pull of an orbiting planet. Instruments like HARPS, High-Accuracy Radial Velocity Planet Searcher, have excelled in detecting planets using this method, particularly massive planets orbiting close to their stars, often referred to as hot Jupiters. Direct imaging, though challenging, provides a way to observe exoplanets by blocking the light of the host star. This technique has captured stunning images of young, massive planets still glowing from the heat of their formation. Other methods, like microlensing and astrometry, have contributed to the growing catalog of exoplanets, each offering unique advantages for studying specific types of systems. The diversity of exoplanets has exceeded all expectations, challenging traditional models of planetary formation. Hot Jupiters, gas giants orbiting closer to their stars than Mercury to the Sun, defy early theories that such planets could only form in the cold outer regions of a star system. Super-Earths, a class of planets larger than Earth but smaller than Neptune, are the most common type of planet discovered so far. Yet they have no equivalent in our solar system. The discovery of planets in the habitable zone regions around stars where conditions might allow liquid water to exist has intensified the search for life beyond Earth. Planets like Kepler 452 billion, sometimes called Earth's cousin, orbit within their stars' habitable zones, raising the tantalizing possibility of environments where life thrive. The TRAPPIST-1 system, with 7 Earth-sized planets orbiting a cool red dwarf star, has captured particular attention, as 3 of its planets lie in the habitable zone. The study of exoplanet atmospheres has become a major focus in the quest to identify potentially habitable worlds. When a planet transits its star, some starlight passes through its atmosphere, allowing astronomers to analyze its composition. Observations with the Hubble Space Telescope, and more recently the James Webb Space Telescope, have detected water vapor, carbon dioxide, methane, and other molecules in exoplanet atmospheres. These findings provide clues about the potential for life and the processes shaping these distant worlds. Biosignatures, chemical markers that indicate the presence of life, are a key target in exoplanet research. Molecules like oxygen, ozone, and methane, when found together in certain proportions, could suggest biological activity. However, interpreting these signals requires caution, as non-biological processes can also produce similar patterns. Advanced instruments and techniques will be needed to distinguish true biosignatures from false positives. The discovery of moons orbiting exoplanets is an emerging frontier in the search for life. Moons like Europa and Enceladus in our solar system, with subsurface oceans beneath icy shells, demonstrate that habitability is not limited to planets. Detecting exomoons remains challenging, but their potential as life-hosting environments makes them an enticing focus for future research. Exomoons could possess stable environments for billions of years, shielded by their host planet's gravitational pull and magnetic field. If they orbit within the habitable zone of their star, or even maintain their own internal heat sources, such as tidal heating, they might harbor conditions favorable for life. Observing these elusive worlds will require refined techniques and more sensitive instruments, but their discovery could significantly expand the scope of our search for extraterrestrial life. As the catalog of known exoplanets grows, astronomers are uncovering new insights into planetary system architecture and the factors that influence their diversity. For instance, superpuffs, planets with masses similar to Earth but with diameters as large as Neptune, challenge current theories of planetary formation and atmospheric retention. Similarly, systems like Kepler 11, with 6 closely packed planets orbiting a single star, show just how varied planetary systems can be compared to our solar system. The study of exoplanets also deepens our understanding of our own origins. By comparing the formation and evolution of other planetary systems, we gain perspective on the uniqueness or lack thereof of our solar system. For example, the discovery of planet migration, where giant planets move inward or outward from their initial orbits, has reshaped our understanding of the solar system's early history. Jupiter's migration likely influenced the asteroid belt and the distribution of water-rich comets, which could have played a role in delivering water to Earth. In addition to addressing fundamental scientific questions, exoplanet research inspires profound philosophical and existential reflections. The discovery of potentially habitable planets, especially those similar to Earth, raises questions about humanity's place in the cosmos. Are we a singular anomaly in the vastness of space, or are planets like ours common, teeming with life at various stages of development? The implications of finding life or confirming its absence extend far beyond science, touching on philosophy, theology, and our understanding of ourselves as a species. Technological advancements are key to pushing the boundaries of exoplanet science. The James Webb Space Telescope, JWST, has already begun providing unprecedented data on the atmospheres of exoplanets, offering glimpses into their chemical makeup. Future missions, such as the European Space Agency's Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, and NASA's Nancy Grace Roman Space Telescope, are poised to further enhance our ability to characterize these distant worlds. Ground-based observatories, equipped with next-generation instruments, will also play a crucial role. The Extremely Large Telescope, ELT, in Chile and the 30-meter telescope, TMT, in Hawaii promise to bring direct imaging of exoplanets into sharper focus, allowing astronomers to study smaller and more distant planets than ever before. These telescopes will provide detailed observations of planetary atmospheres, surface conditions, and even weather patterns, helping to unravel the complexities of alien worlds. One of the most ambitious goals of exoplanet research is to find a true Earth twin, a planet of similar size, composition, and orbital distance from a Sun-like star. Such a discovery would be a milestone in the search for extraterrestrial life, providing a natural laboratory to study how life might arise and evolve under conditions similar to those on Earth. Missions like the LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HAP-X, Habitable Exoplanet Observatory, concepts aim to achieve this goal, with designs capable of imaging Earth-sized planets and searching for biosignatures in their atmospheres. The exploration of exoplanets represents a new era of discovery, one that pushes the limits of human ingenuity and curiosity. Each new world adds to our understanding of the cosmos, revealing its diversity, complexity, and potential for life. As we peer deeper into the universe, we are reminded that the story of planets, stars, and galaxies is also our story and narrative that connects us to the vast expanse of space and time. The search for exoplanets is not merely a quest for scientific knowledge, but a journey of wonder and inspiration. It challenges us to imagine worlds beyond our own and to contemplate the possibility of life elsewhere. With each discovery, we take another step toward answering the age-old question: are we alone in the universe? The question of whether life exists elsewhere is more than a scientific inquiry. It is a profound exploration of our place in the cosmos. Each exoplanet discovery brings us closer to understanding the conditions that might foster life and how those conditions compare to those on Earth. While the search for extraterrestrial life has yet to yield definitive evidence, it continues to push the boundaries of technology, collaboration, and human imagination. One of the most exciting prospects in this search is the detection of biosignatures, chemical markers in the atmosphere of an exoplanet that could indicate the presence of life. Molecules such as oxygen, ozone, methane, and water vapor, especially when found in specific combinations, could suggest biological processes. For example, oxygen and methane are unlikely to coexist in a planet's atmosphere without a continuous replenishment from biological sources, as they react with each other and are eventually depleted. Advanced telescopes, like the James Webb Space Telescope, are already analyzing atmospheric compositions, bringing us closer to finding such biosignatures. Even more tantalizing is the search for technosignatures, indicators of advanced civilizations. These could include artificial lights, industrial pollutants, or unusual energy emissions that cannot be explained by natural processes. While still speculative, the search for technosignatures highlights humanity's enduring curiosity about intelligent life elsewhere in the universe. The study of exoplanets also expands our understanding of habitability. While Earth-like planets in the habitable zone of their stars are a focus, scientists are increasingly considering unconventional environments where life might arise. For instance, planets or moons with subsurface oceans, such as Europa and Enceladus in our solar system, could offer habitable conditions, even without being in the traditional habitable zone. Exoplanets with thick atmospheres or geothermal heating might also host life in unexpected ways, challenging our Earth-centric views of biology. This broader perspective has inspired missions to explore extreme environments on Earth, from hydrothermal vents in the deep ocean to acidic lakes and frozen tundra. These terrestrial analogs provide insights into the resilience of life and its potential to thrive under harsh conditions, guiding the search for life on exoplanets. The quest for exoplanets and extraterrestrial life also raises profound philosophical questions. If we find life elsewhere, how will it reshape our understanding of existence, purpose, and the uniqueness of Earth? Conversely, if we find that life is rare or unique to Earth, what does that mean for humanity's role in the cosmos? These questions underscore the significance of the search, not just as a scientific endeavor, but as a deeply human one. Public engagement plays a critical role in this journey. The discovery of exoplanets has captured the imagination of people worldwide, inspiring awe and curiosity. Programs like NASA's exoplanet exploration and citizen science projects, such as Planet Hunters, allow individuals to participate in the search, fostering a sense of connection to the broader cosmos. These efforts remind us that the exploration of the universe is a shared endeavor, transcending borders and uniting humanity in its quest for knowledge. The future of exoplanet research is boundless, with new technologies and missions on the horizon. The James Webb Space Telescope is just the beginning of a new era of detailed atmospheric studies. Upcoming missions like the European Space Agency's Plato, planetary transits and oscillations of stars, will focus on finding and characterizing Earth-like planets around Sun-like stars. Meanwhile, the development of ground-based observatories, such as the giant Magellan Telescope and the 30-meter telescope, will provide unparalleled resolution and sensitivity, enabling the study of smaller, more distant planets. The search for exoplanets embodies humanity's drive to explore and understand. It is a testament to our ingenuity, perseverance, and capacity for wonder. As we continue to uncover the secrets of these distant worlds, we are reminded of the infinite possibilities that the universe holds and the profound connections that tie us to it. Whether we find life among the stars or not, the journey itself enriches our understanding of the cosmos and our place within it. As we peer into the depths of space, each new discovery becomes a part of our collective story, a story of curiosity, exploration, and the enduring human spirit. The search for other worlds is not just about finding planets or life. It is about discovering ourselves in the vast, interconnected universe we call home. Cosmic phenomena, the universe's most astonishing displays. The universe is a stage for extraordinary phenomena that stretch the limits of human understanding. From cataclysmic explosions to bizarre and unexplained cosmic signals, these events captivate astronomers and challenge our knowledge of physics. Each discovery offers a glimpse into the raw power and complexity of the cosmos, inspiring awe and igniting curiosity about the mechanisms that drive these celestial marvels. One of the most awe-inspiring events in the universe is the supernova, a violent explosion marking the death of a massive star. These stellar outbursts release more energy in a few weeks than the Sun will emit over its entire lifetime. There are several types of supernovae, each with unique causes and characteristics. Core collapse supernovae occur when a massive star exhausts its nuclear fuel, causing its core to collapse under gravity. The resulting explosion ejects the star's outer layers, enriching the surrounding space with heavy elements essential for planet and life formation. Type Iowa supernovae, on the other hand, arise from white dwarfs in binary systems. When a white dwarf accretes enough material from its companion star to exceed a critical mass, it undergoes a thermonuclear explosion. These supernovae serve as standard candles for measuring cosmic distances, playing a pivotal role in the discovery of the universe's accelerated expansion and the existence of dark energy. Even more powerful than supernovae are gamma-ray bursts, GRBs, intense flashes of gamma rays originating from distant galaxies. GRBs are the most energetic events in the universe, releasing as much energy in a few seconds as the Sun will emit in 10 billion years. Long-duration GRBs are thought to result from the collapse of massive stars into black holes, while short-duration GRBs are associated with the merger of neutron stars. The detection of gravitational waves from a neutron star merger in 2017, accompanied by a GRB, confirmed this connection and heralded a new era of multi-messenger astronomy. Another enigmatic cosmic phenomenon is the fast radio burst FREB, a brief and intense burst of radio waves lasting just milliseconds. First discovered in 2007, FRBs remain one of the greatest mysteries in astronomy. While some have been traced to distant galaxies, their exact origins are still debated. Theories range from highly magnetized neutron stars, known as magnetars, to exotic possibilities like signals from advanced extraterrestrial civilizations. Recent detections of repeating FRBs suggest multiple mechanisms may be at play, and ongoing observations aim to unravel their secrets. Pulsars, rapidly rotating neutron stars, are among the universe's most precise natural clocks. These remnants of supernovae emit beams of electromagnetic radiation from their magnetic poles, creating a pulsing effect as they spin. Pulsars are invaluable tools for studying extreme physics, from testing Einstein's general relativity to detecting gravitational waves. Millisecond pulsars, which rotate hundreds of times per second, are particularly remarkable for their stability, rivaling the accuracy of atomic clocks. Quasars, powered by supermassive black holes at the centers of galaxies, are some of the brightest and most distant objects in the universe. These luminous beacons result from the accretion of gas onto the black hole, generating intense radiation as the material spirals inward. Quasars provide insights into the early universe, as their light has traveled billions of years to reach us, carrying information about the conditions and structure of the cosmos in its infancy. The universe also produces more subtle, yet equally fascinating phenomena. Aurorae, the colorful displays of light seen on planets like Earth and Jupiter, occur when charged particles from the solar wind interact with a planet's magnetic field and atmosphere. On Earth, aurorae create breathtaking patterns of green, red, and purple light near the poles, while on Jupiter, they are driven by the planet's intense magnetic field and volcanic activity on its moon Io. Cosmic jets, streams of charged particles ejected at nearly the speed of light, are another mesmerizing phenomenon. These jets are often associated with black holes, neutron stars, and active galactic nuclei. They extend for thousands to millions of light years, influencing their environments by heating surrounding gas and shaping galaxy formation. Observing and modeling these jets help astronomers understand the processes that drive them and their impact on cosmic evolution. The largest structures in the universe, galaxy superclusters and voids, are also sources of wonder. Superclusters, like the Laniakea supercluster that includes the Milky Way, are massive groups of galaxies bound by gravity. They form part of the cosmic web, the vast network of filaments and nodes that defines the universe's large-scale structure. Voids, on the other hand, are regions of space with few galaxies, representing the opposite extreme. These enormous contrasts in density reveal the influence of dark matter and dark energy in shaping the cosmos. Phenomena like these not only challenge our understanding but also inspire technological innovation and international collaboration. Instruments like the Event Horizon Telescope, which captured the first image of a black hole's shadow, and observatories like LIGO and Virgo, which detect gravitational waves, represent the cutting edge of human ingenuity. They allow us to observe events across the electromagnetic spectrum and beyond, opening new windows into the universe. As we continue to explore the cosmos, each phenomenon adds a new chapter to the story of the universe. From the explosive deaths of stars to the faint whispers of distant FRBs, these events remind us of the dynamic and interconnected nature of the cosmos. They also underscore the importance of curiosity, collaboration, and perseverance in uncovering the secrets of existence. The universe's wonders are as endless as its expanse, offering infinite opportunities for discovery and reflection. Whether through the lens of a telescope or the equations of a physicist, the exploration of cosmic phenomena deepens our connection to the universe and our understanding of our place within it. Let me know if you'd like to delve into another celestial marvel or continue expanding on these topics. Dark energy and the expanding universe, the force behind cosmic acceleration. The discovery that the universe is not only expanding but accelerating is one of the most profound revelations in modern cosmology. This phenomenon, driven by a mysterious force known as dark energy, has reshaped our understanding of the cosmos, challenging established theories and raising new questions about the nature of reality. Dark energy, which makes up approximately 68% of the universe's total energy density, governs the universe's large-scale structure and ultimate fate. The story of dark energy begins with the observation of distant Type Iowa supernovae in the late 1990s. Astronomers expected these exploding stars to reveal a slowing expansion due to the gravitational pull of matter. Instead, the supernovae appeared dimmer than expected, indicating they were farther away and that the universe's expansion was accelerating. This unexpected result earned the 2011 Nobel Prize in Physics and introduced the concept of dark energy as the driving force behind this acceleration. Dark energy is fundamentally different from dark matter, which exerts a gravitational pull and contributes to the formation of galaxies and large-scale structures. In contrast, dark energy acts as a repulsive force, counteracting gravity and causing the fabric of space-time to stretch at an ever-increasing rate. The exact nature of dark energy remains one of the greatest mysteries in science, but several leading theories attempt to explain it. The simplest and most widely accepted explanation is the cosmological constant, first introduced by Albert Einstein in his equations of general relativity. Einstein originally added this term to maintain a static universe, unaware of the universe's expansion. After Hubble's discovery of the expanding universe, Einstein discarded the cosmological constant, calling it his greatest blunder. Decades later, the concept was resurrected to explain the observed acceleration, reinterpreted as a property of space itself, an inherent energy density that remains constant as the universe expands. Another intriguing possibility is quintessence, a dynamic scalar field that evolves over time. Unlike the cosmological constant, which is uniform and unchanging, quintessence could vary in strength and density, potentially influencing the universe's expansion rate differently in the past and future. Observations of cosmic acceleration across different epochs may help distinguish between these models. Alternative theories propose modifications to general relativity on cosmic scales. These theories, often grouped under modified gravity, suggest that the effects attributed to dark energy may instead arise from changes in the behavior of gravity at large distances. While these models offer a compelling framework, they face challenges in matching the precision of the cosmological constant's predictions. The evidence for dark energy extends beyond supernova observations. The cosmic microwave background, CMB, a relic of the Surrey universe, provides a snapshot of the universe's energy density and geometry. Measurements of the CMB's temperature fluctuations, particularly those by the Planck satellite, confirm the dominance of dark energy in the current universe. Additionally, baryon acoustic oscillations, BAOs, the imprints of sound waves in the early universe's plasma, serve as standard rulers for measuring cosmic expansion and corroborate the effects of dark energy. Despite its pivotal role, the mechanisms behind dark energy's influence remain enigmatic. One of the greatest puzzles is the cosmological constant problem, which highlights the vast discrepancy between the observed value of dark energy's density and theoretical predictions from quantum field theory. This mismatch, by a factor of 101, 201, 0121, 120, is the largest known disparity between theory and observation in physics, underscoring the need for a deeper understanding of the underlying principles. Dark energy's implications extend to the universe's ultimate fate. If dark energy remains constant, as predicted by the cosmological constant, the universe will continue to expand indefinitely in a scenario known as the Big Freeze. In this future, galaxies will drift farther apart, stars will exhaust their fuel, and the cosmos will grow increasingly cold and dark. Alternatively, if dark energy's strength increases over time, it could lead to a big rip, where the acceleration becomes so extreme that galaxies, stars, and even atoms are torn apart. The search for answers about dark energy is driving the development of cutting-edge observatories and missions. The European Space Agency's Euclid mission, launched to map the distribution of galaxies and dark matter, will provide precise measurements of the effects of dark energy on cosmic structures. NASA's Nancy Grace Roman Space Telescope, set to launch in the coming decade, will combine wide-field imaging and spectroscopy to probe the nature of dark energy and its evolution. Ground-based projects, such as the Vera C. Rubin Observatory, will conduct deep surveys of the night sky, mapping billions of galaxies and detecting supernovae to refine our understanding of cosmic acceleration. These efforts, combined with advanced simulations, will allow scientists to test competing theories and uncover the secrets of dark energy. As we delve deeper into the nature of dark energy, we confront some of the most profound questions about the universe. What is the true nature of this mysterious force? Why does it dominate the universe's energy budget now, rather than earlier or later in cosmic history? And how does it fit into a unified understanding of fundamental physics? These questions push the boundaries of science, connecting cosmology, particle physics, and quantum mechanics. Dark energy is not merely an abstract concept, it is a force shaping the universe on the grandest scales. Its discovery reminds us of the vast unknowns that still await exploration and the power of human curiosity to illuminate the darkest corners of reality. As we seek to unravel its mysteries, we are not just learning about the cosmos, we are redefining our understanding of existence itself. The future of the universe, exploring cosmic endings. The universe's fate has captivated astronomers, physicists, and philosophers for centuries. With the discovery of dark energy and the realization that the universe's expansion is accelerating, our understanding of its possible endings has been transformed. While the ultimate destiny remains uncertain, several scenarios, grounded in the interplay of dark energy, dark matter, and the fundamental laws of physics, outline the potential futures of the cosmos. The Big Freeze is the most widely accepted scenario, based on the assumption that dark energy, as described by the cosmological constant, remains constant over time. In this model, the accelerated expansion of space will continue indefinitely, causing galaxies to drift farther apart. Over billions of years, star formation will cease as galaxies exhaust their gas reserves. Existing stars will age, turning into white dwarfs, neutron stars, or black holes. Planets and moons will grow dark and cold as their parent stars fade. In this scenario, the universe's temperature will approach absolute zero, a state known as heat death. At this point, all energy gradients, the driving force behind physical processes, will vanish. Atoms themselves may decay, leaving a sparse and featureless cosmos populated by black holes and elementary particles. Even black holes, through the slow process of Hawking radiation, will eventually evaporate, leaving behind a vast, dark void. An alternative and more dramatic scenario is the Big Rip. This outcome depends on whether dark energy grows stronger over time, as predicted by some dynamic models like quintessence. In the Big Rip, the repulsive force of dark energy becomes increasingly dominant, overcoming gravity, electromagnetic forces, and even the nuclear forces that bind atoms together. Galaxies would be torn apart, followed by stars, planets, and eventually atoms. Space-time itself would unravel in a catastrophic end. The timeline for the Big Rip varies depending on the model, but it could occur in tens of billions of years if dark energy's strength increases significantly. This scenario would represent not just the end of the universe as we know it, but the dissolution of all structure, down to the most fundamental particles. The Big Crunch is another possibility, though it has become less likely in light of dark energy's discovery. In this model, the expansion of the universe eventually halts and reverses, leading to a contraction driven by gravity. Galaxies, stars, and matter would collide and merge as the universe shrinks. Over time, temperatures would rise as matter becomes increasingly compressed, culminating in a singularity, a point of infinite density similar to the conditions of the Big Bang. The Big Crunch, while dramatic, could also serve as the precursor to a cyclic model of the universe. In this framework, the singularity at the end of the Big Crunch might give rise to a new Big Bang, restarting the cycle of cosmic evolution. Such oscillatory or cyclic models suggest that the universe undergoes endless cycles of expansion and contraction, though this idea faces significant challenges, particularly in reconciling entropy and the observed acceleration of the current universe. A more speculative but intriguing possibility is the Big Bounce, a variation of the cyclic model that avoids a true singularity. In this scenario, the universe contracts to a highly dense state but rebounds into a new phase of expansion. Quantum gravity effects could play a critical role in preventing a singularity, providing a mechanism for the bounce. This idea has gained attention in some approaches to quantum cosmology, such as loop quantum gravity, which proposes that space-time itself has a discrete structure. The heat death, with a twist scenario, introduces the concept of vacuum decay, a possibility rooted in quantum field theory. If the universe's vacuum state is metastable rather than truly stable, it could eventually transition to a lower energy state, initiating a catastrophic chain reaction. This bubble of true vacuum would expand at nearly the speed of light, obliterating everything in its path and reshaping the laws of physics. While unsettling, this scenario is purely speculative and would likely occur on timescales far beyond human comprehension. Each of these scenarios highlights the profound influence of dark energy and the fundamental forces on the universe's ultimate fate. Observations and measurements such as those from the James Webb Space Telescope, Euclid, and the Vera C. Rubin Observatory aim to refine our understanding of dark energy's properties, shedding light on which future the cosmos might face. The fate of the universe also has profound implications for our understanding of existence. If the cosmos ends in a heat death or big freeze, it suggests a gradual fading into oblivion, where the universe becomes devoid of activity and meaning. A big rip or vacuum decay would emphasize the fragility of cosmic structures, while cyclic or bouncing models offer the possibility of renewal and continuity, albeit on incomprehensible time scales. For humanity, contemplating the universe's fate underscores the preciousness of the present. While these cosmic endings lie far beyond any immediate concern, they remind us of the transient nature of all things, from the smallest particles to the grandest galaxies. They also inspire us to seek understanding, to explore, and to appreciate the beauty of the universe while it is still vibrant and alive. The exploration of the universe's destiny is not just a scientific endeavor, but a philosophical and existential journey. It challenges us to consider our place in the cosmos, the nature of time and space, and the ultimate meaning of existence. Whether the universe ends in a whisper or a roar, its story and our story within it will remain a testament to the power of curiosity and the enduring quest for knowledge. Cosmic time scales, the grand journey of the universe. The universe's journey spans an almost incomprehensible range of time scales, from the fraction of a second, following the Big Bang, to the trillions of years that will mark its far future. Exploring these time scales offers a profound perspective on the cosmos, revealing how events that seem instantaneous to us shaped the universe over eons. In the earliest moments after the Big Bang, less than 104,310,43 seconds after the universe's birth, time itself began to unfold. This fleeting instant, known as the Planck epoch, was a period of extraordinary density and temperature. The fundamental forces, gravity, electromagnetism, and the nuclear forces, may have been unified in a single force, governed by laws that quantum gravity seeks to describe. Beyond this epoch, the universe entered the inflationary phase, expanding exponentially in less than 1032 seconds. During this period, quantum fluctuations were stretched into cosmic scales, seeding the formation of galaxies and the large-scale structure. The next critical milestone occurred about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This era, known as recombination, allowed light to travel freely for the first time, producing the cosmic microwave background, CMB. The CMB provides a snapshot of the universe at this early stage, a relic that continues to illuminate the conditions of the primordial cosmos. Over the following hundreds of millions of years, the universe entered the cosmic dark ages. During this time, matter gradually clumped together under the influence of dark matter, forming the first stars and galaxies. These early stars, known as population II stars, were massive and short-lived, synthesizing heavy elements in their cores and dispersing them through supernova explosions. This process set the stage for the formation of subsequent generations of stars and the complex chemistry necessary for planets and life. Around 1 billion years after the Big Bang, the universe transitioned to the epoch of reionization. The radiation from the first stars and galaxies ionized the surrounding hydrogen gas, ending the cosmic dark ages and making the universe transparent to ultraviolet light. Reionization marked the beginning of the cosmic structures we observe today. As galaxies grew and merged into the intricate web of filaments and clusters. On a galactic scale, time flows in billions of years. The Milky Way, for example, has existed for approximately 13.6 billion years, evolving from a protogalactic cloud into the majestic spiral galaxy we inhabit. Galactic collisions and mergers, such as the Milky Way's impending collision with the Andromeda Galaxy in about 4.5 billion years, occur on similarly vast time scales, reshaping the structure of galaxies and triggering bursts of star formation. Stars themselves have life cycles spanning millions to billions of years. A star like the Sun spends roughly 10 billion years fusing hydrogen into helium in its core, a phase known as the main sequence. Massive stars, which burn through their fuel more quickly, may last only a few million years before ending in supernova explosions. Smaller stars, like red dwarfs, can shine for trillions of years, far outlasting the current age of the universe. Looking forward, the universe's time scales stretch into the unfathomable. As dark energy drives the accelerated expansion of space, galaxies beyond the local group will move farther away, becoming invisible to observers within the Milky Way. In 100 trillion years, the era of star formation will end as galaxies deplete their gas reserves. This degenerate era will be dominated by remnants of stars, white dwarfs, neutron stars, and black holes slowly cooling and decaying. On even longer time scales, black holes will dominate the cosmos, slowly evaporating through Hawking radiation over 101, 001, 0101 100 years or more. Eventually, the universe may reach a state of maximum entropy, known as heat death, where no useful energy remains to sustain physical processes. These immense time scales challenge our understanding of time and existence. While human lifetimes are fleeting in comparison, they are part of this grand cosmic timeline, connected to events both ancient and distant. The light we see from distant stars and galaxies carries the history of the universe, linking our moment to the vast expanse of cosmic time. The exploration of these time scales offers not only scientific insights, but also a humbling perspective on our place in the cosmos. By studying the past, present, and future of the universe, we gain a deeper appreciation for the intricate and interconnected processes that have shaped it. The universe's journey is a story of transformation, resilience, and the relentless march of time, a story that continues to unfold with each passing moment. The cosmic microwave background, the universe's faint glow. The cosmic microwave background, CMB, is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the cosmos when it was only 380,000 years old. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the CMB is one of the most significant pieces of evidence supporting the Big Bang theory. It represents the moment when the universe cooled enough for electrons and protons to combine and form neutral atoms, allowing light to travel freely across space for the first time. The CMB is remarkably uniform, with tiny fluctuations in temperature that reflect slight variations in density in the early universe. These density fluctuations served as the seeds for the formation of galaxies, clusters, and other large-scale structures in the cosmos. By studying the CMB, scientists can gain insights into the conditions of the early universe, including its age, composition, and rate of expansion. The precise measurements of the CMB, particularly by missions like the Wilkinson Microwave Anisotropy Probe, MAP, and the Planck satellite, have allowed cosmologists to refine the Big Bang model and improve estimates of key cosmological parameters. One of the most intriguing aspects of the CMB is the presence of a mysterious cold spot, a region of the sky that appears slightly cooler than expected. Some scientists suggest that this cold spot could be the result of a large cosmic void, a region with fewer galaxies and matter than average. Others propose that it might be evidence of a collision between our universe and another bubble universe in the multiverse, although this idea remains speculative. The CMB also provides evidence for the theory of inflation, the rapid expansion of the universe in its first moments. Inflation stretched tiny quantum fluctuations to cosmic scales, creating the density variations seen in the CMB. These variations follow a specific pattern, known as the power spectrum, which matches the predictions of inflationary theory. By analyzing the CMB's power spectrum, scientists have gained insights into the early universe's inflationary phase and the forces that shape the cosmos. In addition to temperature variations, the CMB also exhibits polarization, a property that arises when light is scattered by particles. The polarization of the CMB provides further information about the early universe and has been used to detect the presence of primordial gravitational waves, which are ripples in space-time created during inflation. The search for these gravitational waves is ongoing, as they would provide direct evidence for inflation and a new window into the universe's origins. The CMB serves as a cosmic background, a faint glow that connects us to the beginning of time. By studying this ancient light, we can peer back to the birth of the universe, observing the conditions that set the stage for everything we see today. The CMB is a reminder of the vastness of cosmic history and the journey that matter and energy have taken to form the stars, galaxies, and planets that fill the cosmos. Gamma-ray bursts, the most powerful explosions in the universe. Gamma-ray bursts, GRBs, are the most energetic explosions in the universe, releasing more energy in a few seconds than our sun will emit over its entire 10 billion-year lifetime. Discovered in the 1960s by military satellites designed to detect nuclear explosions, GRBs were initially mysterious. Today, scientists know that these bursts are the result of cataclysmic cosmic events, such as the collapse of massive stars or the merger of neutron stars. GRBs occur in two main types: short-duration bursts, which last less than 2 seconds, and long-duration bursts, which can last from a few seconds to several minutes. Long-duration GRBs are believed to be associated with the deaths of massive stars, which end their lives in spectacular supernovae or hypernovae. When a massive star exhausts its nuclear fuel, its core collapses, forming a black hole or neutron star. The collapse generates powerful jets of gamma rays that shoot out along the star's rotational axis. If one of these jets points toward Earth, we observe a gamma ray burst. Short-duration GRBs, on the other hand, are thought to result from the merger of two neutron stars, or a neutron star and a black hole. These events create intense gravitational waves, as observed by detectors like LIGO and Virgo, followed by a brief but powerful gamma-ray burst. The merger of neutron stars can also produce heavy elements like gold and platinum, which are scattered across space, enriching the cosmos with the building blocks of planets and life. Gamma-ray bursts provide unique insights into the extreme physics of black holes, neutron stars, and the formation of elements. The energy and radiation from GRBs can influence the surrounding environment, potentially affecting nearby star formation and planetary systems. Some scientists have even speculated that a GRB could cause mass extinctions on Earth if it were close enough, as the intense gamma rays could strip away our atmosphere and expose the planet to deadly radiation. The study of GRBs also has practical implications for understanding the structure of the universe. Because GRBs are so bright, they can be seen across vast cosmic distances, serving as beacons that allow astronomers to probe the distant universe. By studying the afterglows of GRBs, scientists can analyze the properties of distant galaxies and measure the expansion rate of the universe. GRBs are thus valuable tools for exploring the early cosmos and understanding the evolution of stars and galaxies. Gamma-ray bursts remind us of the immense power and scale of the universe. They are fleeting, unpredictable, and almost unimaginably violent, yet they play a crucial role in cosmic evolution. Through the study of GRBs, we gain a glimpse into the life cycles of stars, the formation of heavy elements, and the forces that shape the cosmos. Each gamma-ray burst is a reminder of the universe's dynamic nature, a testament to the energy that drives the birth and death of stars across the galaxy. Quantum entanglement, spooky action at a distance. Quantum entanglement is a phenomenon in which particles become interconnected in such a way that the state of one particle instantly influences the state of the other, regardless of the distance between them. First described by physicist Albert Einstein as spooky action at a distance, entanglement challenges our conventional understanding of locality and causality, suggesting that particles can be linked across space in ways that defy classical physics. In quantum entanglement, pairs of particles are created in such a way that their properties are correlated. If one particle is measured and found to have a particular property, such as spin, the other particle will instantly have the opposite property, even if they are light years apart. This instantaneous connection occurs faster than the speed of light, violating the usual constraints of special relativity and suggesting that information might travel in ways we do not fully understand. Entanglement plays a central role in quantum mechanics and has led to the development of quantum information science. In quantum computing, for instance, entanglement is used to create qubits that can perform calculations far faster than classical bits. Entangled qubits enable quantum computers to solve complex problems in seconds that would take classical computers years or even centuries. Quantum entanglement also forms the basis for quantum cryptography, which offers theoretically unbreakable encryption by using entangled particles to create secure communication channels. Quantum entanglement has been experimentally verified in numerous tests, including those involving Bell's theorem, which demonstrates that particles can exhibit correlations that cannot be explained by any local hidden variables. This result confirms the non-local nature of quantum mechanics and suggests that our classical intuitions about space and separation do not apply at the quantum level. Entanglement raises profound questions about the nature of reality and the limits of knowledge. Some interpretations of quantum mechanics, such as the many worlds interpretation, propose that entanglement reflects a branching of possible realities, where each measurement creates a new world in which different outcomes occur. Others suggest that entanglement reveals a deeper level of interconnectedness in the universe, challenging the notion that objects are truly separate from one another. Quantum entanglement pushes the boundaries of physics, offering a glimpse into the fundamental nature of reality. By studying entanglement, scientists are developing technologies that may revolutionize computing, communication, and even our understanding of consciousness. Entanglement is a reminder that the universe is far stranger and more interconnected than we might imagine. A world where particles communicate across vast distances, revealing the mysterious and hidden structure of the cosmos. Neutron stars, cosmic giants compressed into tiny volumes. Neutron stars are one of the most extreme and fascinating objects in the universe. Formed from the collapsed core of a massive star that has gone supernova, a neutron star contains a mass greater than that of the Sun, compressed into a sphere only about 20 kilometers in diameter. This immense density results in gravitational forces so strong that atoms themselves collapse, leaving a core composed almost entirely of neutrons, the particles found within atomic nuclei. The density of a neutron star is staggering. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. This incredible density also gives neutron stars some of the strongest magnetic fields in the universe, with magnetic strengths millions or even billions of times greater than that of Earth. These intense magnetic fields generate powerful radiation and can influence the surrounding space for hundreds of kilometers. Neutron stars exhibit extraordinary behavior, including rapid rotation. Some neutron stars spin hundreds of times per second, a phenomenon that results from the conservation of angular momentum. When a massive star collapses, its rotation speeds up as it becomes more compact, much like a figure skater pulling in their arms during a spin. The fastest known neutron stars, known as millisecond pulsars, rotate so quickly that they complete a full rotation in a fraction of a second. Some neutron stars are also pulsars, emitting beams of electromagnetic radiation from their magnetic poles. As the pulsar rotates, these beams sweep across space like a cosmic lighthouse, creating a pulsing effect as seen from Earth. Pulsars have extremely precise rotational periods, making them some of the most reliable clocks in the universe. This precision has enabled scientists to use pulsars for tests of general relativity, and even to search for gravitational waves. Another class of neutron stars, called magnetars, have even more extreme magnetic fields, sometimes as much as 1,000,000,000 times stronger than Earth's. These powerful fields can cause star quakes on the surface of the magnetar, releasing massive amounts of X-rays and gamma rays. In rare cases, magnetars can produce giant flares, energetic outbursts that release as much energy in a few seconds as the Sun emits in 100,000 years. The study of neutron stars offers insights into the nature of matter under extreme conditions. Since neutron stars are composed of nuclear matter at densities far greater than anything on Earth, they provide a unique laboratory for studying the behavior of particles at extreme densities and pressures. Some theories even suggest that the cores of neutron stars may contain exotic forms of matter, such as quark-gluon plasma, where the quarks that make up protons and neutrons are no longer bound together. Neutron stars are reminders of the universe's incredible diversity and the extremes to which matter can be pushed. They challenge our understanding of physics, revealing the complex interplay between gravity, quantum mechanics, and nuclear forces. By studying these dense remnants of stellar explosions, we gain insights into the life cycles of stars, the formation of heavy elements, and the mysteries of nuclear matter. The cosmological constant, Einstein's blunder and dark energy's rise. The cosmological constant is one of the most intriguing and mysterious aspects of modern cosmology. Originally introduced by Albert Einstein in 1917 as a fudge factor to allow for a static universe, the cosmological constant was meant to counteract the effects of gravity and prevent the universe from collapsing. However, when evidence emerged that the universe was expanding, Einstein famously abandoned the cosmological constant, reportedly calling it his greatest blunder. Decades later, the cosmological constant made a surprising comeback with the discovery of dark energy. In the 1990s, astronomers studying distant supernovae found that the universe's expansion was accelerating, a discovery that defied expectations. To explain this accelerated expansion, scientists reintroduced the cosmological constant, this time as a form of dark energy, a mysterious force that counteracts gravity on large scales and drives the expansion of space. The cosmological constant is now considered a measure of the energy density of empty space, or vacuum energy. According to quantum field theory, even a perfect vacuum is filled with virtual particles that pop in and out of existence, creating a small but persistent energy. This vacuum energy exerts a repulsive force that counteracts gravity, leading to an accelerated expansion of the universe. Despite its success in explaining dark energy, the cosmological constant presents a significant challenge for theoretical physics. Calculations of vacuum energy based on quantum mechanics suggest a value that is far greater than what we observe, a discrepancy known as the cosmological constant problem. This discrepancy, which spans over 100 orders of magnitude, remains one of the most profound puzzles in physics, suggesting that our understanding of quantum mechanics, gravity, or both may be incomplete. The cosmological constant also has profound implications for the future of the universe. If dark energy continues to dominate, the universe will keep expanding at an accelerated rate, leading to a scenario known as the Big Freeze or heat death, where galaxies drift apart, stars burn out, and the cosmos becomes cold and dark. In this vision of the future, the universe would reach a state of maximum entropy, with little or no energy available to support life or complex structures. The cosmological constant challenges our understanding of fundamental forces and the nature of space itself. It represents the tension between quantum mechanics and general relativity, highlighting the need for a unified theory of quantum gravity. Whether the cosmological constant is a true constant or a dynamic field, like quintessence, remains an open question. But it continues to inspire research into the mysteries of dark energy and the fate of the cosmos. Multi-messenger astronomy, listening to the universe's signals. Multi-messenger astronomy is a revolutionary approach to studying the cosmos that combines observations of light, gravitational waves, neutrinos, and cosmic rays. By observing the universe through multiple messengers, scientists can gain a more complete picture of cosmic events, from the collisions of black holes to the explosions of supernovae. This approach marks a new era in astronomy, allowing researchers to study the same phenomena from different perspectives and unlock previously hidden aspects of the universe. One of the first major breakthroughs in multi-messenger astronomy occurred in 2017, when astronomers observed a collision between two neutron stars. This event, known as GU 17817, was detected by gravitational wave observatories LIGO and Virgo, and was followed by observations across the electromagnetic spectrum, including X-rays, radio waves, and visible light. The detection of gravitational waves and light from the same event provided a wealth of information, confirming theories about neutron star mergers and revealing the origins of heavy elements like gold and platinum. Multi-messenger astronomy relies on a diverse set of observatories and detectors. Gravitational wave observatories like LIGO and Virgo detect ripples in space-time caused by massive cosmic events, while neutrino observatories, such as IceCube in Antarctica, detect high-energy neutrinos produced by supernovae, gamma-ray bursts, and active galactic nuclei. By combining these signals with traditional electromagnetic observations, scientists can explore the universe in unprecedented detail. Each messenger carries unique information. Gravitational waves reveal information about the masses, spins, and distances of merging black holes and neutron stars, while neutrinos offer insights into the processes occurring in supernovae and other high-energy environments. Cosmic rays, high-energy particles that travel through space, provide clues about the origins of astrophysical phenomena, although their paths are deflected by magnetic fields, making it difficult to trace them back to their sources. Multi-messenger astronomy has the potential to answer some of the biggest questions in astrophysics. For instance, by studying the origins of cosmic rays and neutrinos, scientists hope to learn more about the environments around supermassive black holes and the processes that power active galactic nuclei. Multi-messenger observations could also reveal the mechanisms behind the formation of heavy elements and the distribution of matter in the universe. The field of multi-messenger astronomy is still in its early stages, but each new observation brings us closer to a deeper understanding of the cosmos. By combining different types of signals, scientists can uncover hidden aspects of the universe, opening new windows into the nature of gravity, the behavior of particles, and the forces that drive cosmic evolution. Multi-messenger astronomy represents a convergence of technologies and theories, uniting our observations into a comprehensive view of the universe. The observable universe and its boundaries. When we talk about the universe, we are often referring to the observable universe, the region of space from which light has had time to reach us since the Big Bang. This observable universe spans a radius of about 46 billion light-years, encompassing all the stars, galaxies, and cosmic structures we can observe. However, the universe may extend far beyond what we can see, possibly infinitely, containing countless galaxies and realms beyond our current reach. The observable universe is limited by the speed of light and the finite age of the universe. Since the universe is about 13.8 billion years old, we can only see objects whose light has traveled for 13.8 billion years or less. However, due to the expansion of space, these objects are now much farther away than their light travel time would suggest, resulting in an observable universe with a diameter of about 93 billion light-years. The concept of an observable universe raises questions about what lies beyond its boundaries. Since we cannot observe regions beyond this horizon, we do not know whether the universe is finite or infinite. If it is infinite, there could be an endless number of galaxies, stars, and possibly even other versions of Earth, each located at extreme distances beyond our view. In this case, the observable universe would be just a small fraction of an endless cosmic landscape. The boundary of the observable universe also introduces the concept of a cosmic light horizon, beyond which we cannot receive any information. This horizon limits our knowledge of the cosmos and poses challenges for cosmology, as certain regions of the universe are permanently beyond our reach. Some theories, such as inflation, suggest that the observable universe is part of a larger multiverse, with other bubble universes existing beyond our cosmic horizon. Exploring the observable universe allows scientists to study the large-scale structure of the cosmos, the distribution of galaxies, and the forces that shape cosmic evolution. By examining distant galaxies, we can look back in time, observing the universe as it was billions of years ago. These observations provide clues about the universe's history, from the formation of the first stars to the growth of galaxy clusters and superclusters. The observable universe challenges us to confront the limitations of human perception and the vastness of cosmic time. Every point of light we see represents a journey through space and time, a connection to the distant past and the unimaginable distances that define our place in the cosmos. Whether or not the universe extends infinitely beyond what we can observe, the concept of the observable universe reminds us of the boundless mysteries that lie beyond our reach. Cosmic strings. Theoretical relics from the early universe. Cosmic strings are hypothetical one-dimensional defects in the fabric of space-time that may have formed in the early universe during phase transitions, as the cosmos cooled after the Big Bang. Similar to cracks that appear when water freezes into ice, cosmic strings are thought to be cracks or fault lines in space-time, resulting from shifts in the universe's fundamental fields. These objects, if they exist, would be extremely thin yet incredibly dense, with a single cosmic string possibly containing as much mass as a galaxy within a width narrower than a proton. Cosmic strings are fascinating because they represent a bridge between particle physics and cosmology. These theoretical structures are predicted by certain models of high-energy physics, particularly in the context of grand unified theories, GUTs, that attempt to unify the forces of nature. If cosmic strings exist, they could provide insights into the state of the universe in its earliest moments, offering a glimpse into the conditions that preceded the formation of galaxies and other cosmic structures. One of the unique features of cosmic strings is their potential to produce gravitational waves. As they oscillate, vibrate, or loop around, cosmic strings could emit gravitational radiation detectable by observatories like LIGO and Virgo. Some cosmic strings might even reconnect with themselves, forming loops that decay over time and emit bursts of gravitational waves. Detecting such waves would provide not only evidence for cosmic strings, but also insights into the physics of the early universe. Cosmic strings might also create lensing effects, bending the light of distant stars and galaxies. If a cosmic string passes in front of a distant light source, it could create a distinctive line-shaped gravitational lens, distinguishing it from the more circular lensing caused by massive objects like galaxies and clusters. Astronomers searching for these unusual lensing patterns hope to detect cosmic strings and gain a better understanding of the universe's underlying structure. The existence of cosmic strings remains speculative, but they offer an intriguing avenue for exploring the early universe. If discovered, cosmic strings would represent a new form of matter energy, distinct from anything observed so far, and would open up new possibilities for understanding space-time, gravity, and the fundamental forces that shape the cosmos. Tachyons, hypothetical particles beyond the speed of light. Tachyons are hypothetical particles that, if they exist, would travel faster than the speed of light. According to special relativity, particles with mass require infinite energy to reach the speed of light, making it impossible for ordinary particles to achieve or surpass this limit. However, tachyons would have imaginary mass and could theoretically exist only at superluminal, faster than light, speeds, never slowing down to or below the speed of light. Their existence would challenge our understanding of causality, space-time, and the nature of reality itself. The concept of tachyons arises from the mathematics of relativity. In certain equations, solutions exist for particles with imaginary mass that move faster than light. While these particles have never been observed, tachyons continue to be a subject of theoretical interest. They appear in certain quantum field theories and are sometimes used in speculative models of the universe's fundamental structure. If tachyons exist, they could have profound implications for causality. Tachyons could potentially allow information to be transmitted faster than light, raising the possibility of time paradoxes, such as sending a signal back in time. This potential to violate causality has made tachyons a controversial topic, as they challenge one of the foundational principles of modern physics, the notion that cause precedes effect. Some theories suggest that tachyons might play a role in quantum mechanics, where certain spooky phenomena, like quantum entanglement, appear to involve faster-than-light connections between particles. While there is no direct evidence linking tachyons to quantum mechanics, their theoretical existence sparks intriguing discussions about the nature of information, communication, and the limits of knowledge in the universe. Tachyons remain speculative, and no evidence has been found for their existence. Yet they serve as a fascinating thought experiment, challenging our understanding of space-time and raising questions about the ultimate speed limits in the universe.
32 seconds into the flight.
Tachyons remind us of the boldness of theoretical physics, where concepts are explored not just for their immediate practicality, but for their ability to expand our imaginations and redefine what is possible. Hawking radiation, black holes' mysterious glow. Hawking radiation is a theoretical prediction made by physicist Stephen Hawking in 1974, suggesting that black holes are not entirely black but emit a faint radiation due to quantum effects near their event horizons. This radiation arises from particle-antiparticle pairs that form near the event horizon, with one particle falling into the black hole and the other escaping into space. Over time, this radiation causes the black hole to lose mass and eventually evaporate, challenging the classical view that nothing can escape a black hole's gravitational grid. Hawking's discovery revolutionized our understanding of black holes, showing that they are not entirely isolated objects, but instead interact with the quantum vacuum around them. According to Hawking's theory, black holes are subject to entropy, a measure of disorder, and therefore must obey the second law of thermodynamics. This insight led to the formulation of black hole thermodynamics, which describes the relationship between a black hole's surface area, entropy, and temperature. Hawking radiation has profound implications for the nature of information and the structure of space-time. The gradual evaporation of black holes raises the question of what happens to the information contained within them. According to quantum mechanics, information cannot be destroyed. Yet Hawking radiation suggests that black holes eventually vanish, taking all the information they contained with them. This paradox, known as the black hole information paradox, has sparked decades of debate and research in theoretical physics. The information paradox has led to various proposed solutions, including the possibility that information is encoded on the event horizon of the black hole in a holographic manner. This idea aligns with the holographic principle, suggesting that the three-dimensional information inside a black hole might be preserved on its two-dimensional surface. Other theories propose that information could be preserved in baby universes, or that quantum gravity effects allow for the escape of information in ways not yet understood. Hawking radiation remains a theoretical prediction, as it is incredibly faint and difficult to detect. For a stellar mass black hole, the temperature of Hawking radiation would be far below the cosmic microwave background, making it practically invisible. However, if micro-black holes, tiny black holes with much smaller masses exist, they could emit detectable Hawking radiation before evaporating completely. Experiments at high-energy particle colliders may one day create such black holes, offering a way to observe Hawking radiation directly. Hawking radiation is a reminder of the profound mysteries that lie at the intersection of quantum mechanics and gravity. It challenges us to rethink our assumptions about black holes, information, and the limits of knowledge. While it remains a theoretical concept, Hawking radiation continues to inspire new research and pushes us closer to a deeper understanding of the cosmos. Redshift and the expansion of the universe. Redshift is the phenomenon where light from distant objects appears shifted toward the red end of the spectrum. This effect occurs when an object moves away from us, causing the light waves to stretch and lengthen. Redshift is a crucial tool in cosmology, as it provides evidence for the expansion of the universe, and allows scientists to measure the speed at which galaxies are receding from us. The discovery of redshift in the light from distant galaxies was a groundbreaking moment in astronomy. In the 1920s, astronomer Edwin Hubble observed that galaxies are moving away from us, and that the farther away they are, the faster they recede. This observation, known as Hubble's law, provided strong evidence that the universe is expanding and laid the foundation for the Big Bang theory. Redshift is caused by the Doppler effect for nearby objects, where the motion of an object through space affects the wavelength of light. For objects at greater distances, however, redshift is primarily due to the expansion of space itself. As space expands, it stretches the light traveling through it, causing distant galaxies to appear redder than they would in a static universe. This cosmological redshift is a direct result of the universe's expansion and is one of the key pieces of evidence supporting the Big Bang model. Redshift allows astronomers to estimate the distances of galaxies and to map the large-scale structure of the universe. By measuring the redshift of light from galaxies and clusters, scientists can determine their speed and direction, revealing patterns in the distribution of matter across cosmic scales. Redshift surveys have led to the discovery of structures like the cosmic web, the vast network of filaments and voids that connects galaxies across billions of light years. Redshift is also essential for studying the history of the universe. Because light from distant galaxies takes time to reach us, observing high redshift galaxies allows us to look back in time and study the universe as it appeared billions of years ago. By analyzing these early galaxies, scientists gain insights into the formation of stars, the evolution of galaxies, and the processes that shaped the cosmos in its youth. Redshift has applications beyond cosmology as well. It helps astronomers study the properties of stars, the rotation of galaxies, and even the motion of planets within our solar system. The study of redshift provides a link between the motion of celestial objects and the fabric of space itself, offering insights into the universe's past, present, and future. As one of the foundational tools of cosmology, redshift reminds us of the interconnectedness of light, motion, and time. Each redshifted photon tells a story of the universe's expansion, the journey of galaxies across space, and the passage of cosmic time. Through redshift, we witness the dynamic nature of the cosmos, a universe in constant motion, evolving and expanding over billions of years. The EPR paradox and quantum reality. The EPR paradox, named after physicists Einstein, Podolsky, and Rosen, is a thought experiment that challenges the completeness of quantum mechanics. In 1935, Einstein and his colleagues proposed the paradox to highlight what they saw as a flaw in quantum theory. They argued that if quantum mechanics were complete, it would allow for spooky action at a distance, where measurements of one particle could instantaneously affect another, even if they were far apart. The EPR paradox centers on the concept of quantum entanglement, where two particles become interconnected, or entangled, in such a way that the state one particle determines the state of the other. According to quantum mechanics, this connection occurs instantaneously, regardless of distance, which seems to violate the principle that nothing can travel faster than light. Einstein and his colleagues argued that this non-local effect suggested that quantum mechanics was incomplete and that hidden variables might account for the apparent randomness in quantum systems. The EPR paradox led to decades of debate about the nature of quantum reality. In the 1960s, physicist John Bell developed a mathematical inequality known as Bell's theorem to test whether hidden variables could explain quantum correlations. Experiments to test Bell's theorem showed that entangled particles exhibit correlations that cannot be explained by any local hidden variables, supporting the idea that quantum mechanics is inherently non-local. The resolution of the EPR paradox has profound implications for our understanding of reality. It suggests that particles can be connected in ways that transcend classical physics, challenging our notions of space, causality, and separation. The EPR paradox and Bell's theorem have also inspired new fields of research, such as quantum information science, which seeks to harness entanglement for technologies like quantum computing and secure communication. The EPR paradox remains a cornerstone of quantum mechanics, highlighting the mysteries of entanglement and the limits of our understanding. It reminds us that the universe may operate in ways that defy classical logic, revealing a deeper interconnectedness between particles, information, and reality itself. Quasars, the beacons of the distant universe. Quasars, or quasi-stellar objects, are among the most luminous and energetic objects in the universe, powered by supermassive black holes at the centers of distant galaxies. These black holes, which can be billions of times more massive than the Sun, generate intense energy as they consume surrounding gas and dust. This material forms an accretion disk around the black hole, where it heats up due to friction, releasing vast amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays. Discovered in the 1960s, quasars were initially mistaken for stars due to their point-like appearance. However, their immense luminosity and redshift revealed that they were not stars within our galaxy, but rather incredibly distant objects billions of light years away. Quasars are so bright that they can outshine the galaxies that host them, and they serve as cosmic lighthouses, illuminating the far reaches of the universe and providing a glimpse into its early stages. Quasars are essential tools for studying the early universe, as they are typically found at great distances, meaning their light has traveled billions of years to reach us. Observing quasars allows astronomers to look back in time to a period when galaxies and black holes were first forming. The presence of supermassive black holes powering quasars in the early universe suggests that these black holes formed rapidly, although the mechanisms behind their rapid growth remain a mystery. Quasars also help scientists study the large-scale structure of the universe. The light from quasars passes through clouds of gas and intergalactic matter on its way to Earth, revealing absorption lines in the quasar's spectrum. By analyzing these lines, astronomers can map the distribution of matter in the universe, including hydrogen gas and other elements. This technique, known as quasar absorption line spectroscopy, provides insights into the distribution of dark matter, the formation of galaxies, and the evolution of cosmic structures. One of the most intriguing aspects of quasars is their variability. Some quasars exhibit changes in brightness over short periods, indicating fluctuations in the accretion disk around the black hole. These variations provide clues about the dynamics of matter falling into black holes and the processes that govern their energy output. Studying quasar variability has helped astronomers refine models of accretion and gain a better understanding of the extreme environments near black holes. Quasars remind us of the power and scale of the universe. These cosmic beacons, visible across billions of light years, reveal the early stages of galaxy formation and the growth of black holes. As one of the most luminous objects in the cosmos, quasars continue to captivate astronomers and inspire questions about the origins and evolution of the universe. The observable universe's horizon, the edge we can never reach. The observable universe is limited by what we can see based on the speed of light and the universe's age. This limit forms the cosmic horizon, a boundary beyond which we cannot observe because light from those regions has not had enough time to reach us since the beginning of the universe. Although the universe itself may be much larger, possibly even infinite, the observable universe is confined to a radius of about 46 billion light-years. The cosmic horizon is an inherent limit to our knowledge of the universe. As the universe expands, distant galaxies recede from us, and those near the edge of the observable universe are moving away faster than the speed of light. This means that, beyond a certain point, galaxies are receding so quickly that their light can never reach us, effectively placing them beyond our reach forever. The concept of a cosmic horizon also raises questions about what lies beyond. If the universe is infinite, there could be galaxies, stars, and planets beyond the observable limit, extending endlessly. However, since we cannot observe these regions, we can only speculate about their properties. Some theories suggest that regions beyond our horizon may have different physical laws or constants, creating bubble universes within a larger multiverse. The cosmic horizon is not a fixed boundary. As the universe ages, the horizon will expand, allowing us to observe previously unseen regions. However, because the universe's expansion is accelerating due to dark energy, some distant galaxies that are currently observable will eventually move beyond our cosmic horizon, disappearing from view. This phenomenon suggests that the universe's observable content will gradually diminish over trillions of years, leaving future observers in a relatively empty and isolated cosmos. The cosmic horizon challenges us to confront the limits of observation and the vastness of the unknown. It reminds us that, despite the immense scale of the observable universe, it may be only a small fraction of a much larger reality. The horizon defines the edge of human knowledge, marking the boundary between what we can study and what lies forever beyond our reach. The baryon asymmetry problem. Why is there more matter than antimatter? The baryon asymmetry problem is one of the major unsolved mysteries in cosmology and particle physics. According to our current understanding of the Big Bang, matter and antimatter should have been created in equal amounts. However, observations show that the universe is dominated by matter, with very little antimatter present. This discrepancy suggests that some unknown process caused a slight imbalance, allowing matter to prevail over antimatter and form the galaxies, stars, and planets we observe today. Antimatter is the counterpart to matter, with each particle of matter having an antimatter equivalent. For instance, the electron has a counterpart called the positron, which has the same mass but an opposite charge. When a particle of matter meets its antimatter counterpart, they annihilate each other, releasing energy in the form of photons. If equal amounts of matter and antimatter had existed in the early universe, they would have annihilated each other completely, leaving behind a universe filled only with radiation. To explain the dominance of matter, scientists propose that a small asymmetry must have existed in the early universe, allowing matter to outnumber antimatter entirely. This asymmetry could have arisen from CP violation, a phenomenon in which certain particles and their antiparticles behave differently. CP violation has been observed in laboratory experiments, but the observed effect is not large enough to account for the amount of matter in the universe. This suggests that additional, unknown processes may be responsible for the imbalance. The baryon asymmetry problem has profound implications for understanding the laws of physics. It suggests that the early universe was governed by conditions or forces that have yet to be fully understood. Solving this mystery could reveal new insights into the nature of particles, forces, and the evolution of the cosmos. Researchers are investigating possible explanations, including theories involving heavy particles, new forces, and even interactions with dark matter. The study of baryon asymmetry is also linked to experiments in particle physics, such as those conducted at the Large Hadron Collider, LHC. By recreating the high-energy conditions of the early universe, scientists hope to observe new particles or interactions that could shed light on the origin of matter-antimatter asymmetry. Discovering the cause of this imbalance would not only explain why we exist, but would also deepen our understanding of the universe's fundamental nature. Superfluid helium and the study of quantum fluids. Superfluid helium is a phase of helium that occurs at temperatures near absolute zero, where the liquid helium exhibits unique and seemingly impossible properties. When helium is cooled to temperatures below 2.17 Kelvin, it undergoes a transition into a superfluid state, where it flows without friction or viscosity. This lack of friction allows superfluid helium to do things that defy conventional physics, such as climbing up the walls of its container or flowing through narrow channels without any resistance. The behavior of superfluid helium provides a glimpse into the quantum mechanical properties of matter. Unlike ordinary fluids, superfluid helium exhibits quantum coherence, meaning that all helium atoms in the fluid occupy the same quantum state. This collective behavior gives rise to phenomena like the formation of quantized vortices, where the fluid rotates in discrete, quantized units rather than in a continuous flow. One of the most remarkable properties of superfluid helium is its ability to form a thin film that flows up and over the edges of a container, seemingly defying gravity. This phenomenon, known as Rowland film formation, occurs because the superfluid seeks to maintain a constant thickness across its surface. The film spreads out over the container, creating a fountain effect as the superfluid moves without resistance. The study of superfluid helium has led to new insights in condensed matter physics and has inspired research into other forms of quantum fluids, such as Bose-Einstein condensates. These states of matter provide valuable models for understanding quantum mechanics on a macroscopic scale, where the effects of quantum behavior become visible. Superfluid helium also serves as an analog for understanding other complex systems, including the behavior of electrons in superconductors and the properties of neutron stars, where similar quantum effects are thought to occur. Superfluid helium is not just a scientific curiosity. It represents a window into the quantum world and a reminder that matter behaves in ways that challenge our classical intuitions. By studying superfluids, scientists gain insights into the fundamental nature of quantum mechanics and the strange behaviors that emerge at ultra-low temperatures. Cosmic rays, high-energy particles from outer space. Cosmic rays are high-energy particles that travel through space, bombarding Earth from all directions. These particles, primarily protons and atomic nuclei, originate from sources both within and outside our galaxy, including supernovae, neutron stars, and active galactic nuclei. When cosmic rays collide with the Earth's atmosphere, they produce a cascade of secondary particles, creating showers of particles that can reach the ground. Cosmic rays were first discovered in the early 20th century, and they continue to be a subject of intense study due to their mysterious origins and extreme energies. Some cosmic rays, known as ultra-high-energy cosmic rays, have energies millions of times greater than those produced in human-made particle accelerators. The sources of these extreme cosmic rays remain unknown, but they are thought to originate from powerful astrophysical events such as supernova explosions, black hole jets, or collisions between galaxy clusters. Cosmic rays provide valuable information about high-energy processes in the universe. By studying the composition and energy of cosmic rays, scientists can learn about the environments and forces that accelerate particles to such extreme speeds. Cosmic rays also provide insights into magnetic fields in our galaxy, as these fields affect the paths of charged particles, making it difficult to trace cosmic rays back to their origins. Cosmic rays pose challenges for both astronauts and technology. High-energy particles can penetrate spacecraft and human tissue, posing health risks for astronauts on long-duration missions beyond Earth's protective atmosphere. On Earth, cosmic rays can interfere with electronic systems, particularly in high-altitude environments, leading to glitches in aircraft and even affecting computer memory. Despite these challenges, cosmic rays remain a vital tool for understanding the high-energy universe. Observatories such as the Pierre Auger Observatory in Argentina are dedicated to detecting and analyzing cosmic rays, helping to map their origins and properties. By studying cosmic rays, we gain insights into the universe's most powerful forces, from supernovae to active galaxies, and explore the limits of energy in the cosmos. Gravitational lensing, the cosmic magnifying glass. Gravitational lensing is a phenomenon where the gravity of a massive object, like a galaxy or galaxy cluster, bends the light of objects behind it. This effect, predicted by Einstein's general theory of relativity, acts like a cosmic magnifying glass, distorting, magnifying, and even creating multiple images of distant galaxies or quasars. Gravitational lensing has become a powerful tool in astronomy, allowing scientists to study objects that would otherwise be too faint or distant to observe. There are two main types of gravitational lensing: strong lensing and weak lensing. Strong lensing occurs when the foreground object is massive enough to create multiple distinct images of the background object, sometimes forming spectacular Einstein rings, where light appears in a circular shape around the lensing mass. Weak lensing, on the other hand, creates more subtle distortions, slightly warping the shape of background galaxies. By analyzing these distortions, astronomers can map the distribution of dark matter, which doesn't emit light but has gravitational effects on surrounding space. Gravitational lensing offers unique insights into the structure of the universe. By studying the way light is bent, astronomers can measure the mass of galaxy clusters, including the dark matter within them. This technique has revealed that dark matter makes up most of the mass in these clusters, providing strong evidence for its existence. Lensing also allows scientists to observe extremely distant objects by magnifying their light, giving us a glimpse into the universe's past, shortly after the Big Bang. One of the most fascinating applications of gravitational lensing is its use in studying the large-scale structure of the cosmos. Weak lensing surveys, such as those conducted by the Dark Energy Survey (DS) and the upcoming Euclid mission, map the distribution of dark matter on cosmic scales, helping scientists understand how galaxies and clusters are arranged in the cosmic web. These surveys also provide information about dark energy by measuring how lensing patterns evolve over time, revealing the expansion history of the universe. Gravitational lensing is a reminder of the interplay between light and gravity, two forces that shape our view of the cosmos. It allows us to peer deeper into space, observe the unseen, and uncover the hidden structure of the universe. Each gravitational lens is a natural telescope, a window into distant galaxies and the invisible mass that binds them together. Black hole mergers, the dance of titans. Black hole mergers are some of the most powerful events in the universe, releasing immense amounts of energy in the form of gravitational waves ripples in the fabric of space-time. When two black holes orbit each other, they gradually spiral closer due to energy loss from gravitational wave emission. This process accelerates until the black holes collide and merge, creating a single, larger black hole. The energy released in this final stage is equivalent to the mass of several suns, radiated outward in gravitational waves detectable across billions of light years. The detection of gravitational waves from black hole mergers, first achieved by the LIGO Laser Interferometer Gravitational Wave Observatory and Virgo collaborations in 2015, opened a new era in astrophysics. These observations allow scientists to study black holes in ways that were previously impossible, providing information about their masses, spins, and origins. Gravitational waves offer a soundtrack of the universe's most extreme events, capturing the echoes of black hole mergers, neutron-star collisions, and other cataclysmic phenomena. Black hole mergers are thought to occur in two main environments: isolated binaries, where two black holes form from a pair of massive stars, and dense star clusters, where interactions between stars and black holes can lead to mergers. Studying these events helps scientists understand the evolution of massive stars, the role of stellar clusters, and the population of black holes in the universe. Each merger provides a unique data point in understanding how black holes form and grow. The merger of black holes also sheds light on the concept of spins. Black holes can have angular momentum, or spin, depending on how they were formed. When two black holes merge, their spins interact, affecting the final spin of the resulting black hole and the pattern of gravitational waves emitted. By analyzing these waveforms, scientists can infer the spins of the original black holes, providing clues about their history and formation pathways. Black hole mergers are more than just cosmic collisions. They are windows into the fundamental nature of space-time and gravity. As gravitational wave observatories continue to improve, we may one day detect hundreds or thousands of these events, creating a gravitational wave sky that reveals the hidden dance of black holes across the cosmos. These observations push the boundaries of human knowledge, offering a new way to explore the universe and challenging our understanding of the most mysterious objects in existence. The large-scale structure of the universe, the cosmic web. The universe is not a random scattering of galaxies. It has a large-scale structure known as the cosmic web, a vast network of filaments, clusters, and voids that stretches across billions of light years. This structure is shaped by dark matter, gravity, and the expansion of the universe, with galaxies and clusters forming along the densest regions of the web. The cosmic web reveals how matter is distributed on the largest scales, connecting galaxies in an intricate pattern that resembles a vast, interconnected spider web. The formation of the cosmic web is a result of tiny fluctuations in the density of matter in the early universe. After the Big Bang, slight variations in density caused matter to clump together, forming regions of higher and lower density. Over billions of years, these initial fluctuations grew due to gravitational attraction, eventually leading to the formation of galaxies, clusters, and the filaments that connect them. The cosmic web is a testament to the power of gravity, shaping the universe on scales far beyond individual galaxies. Observing the cosmic web allows scientists to test models of dark matter and dark energy, the mysterious components that make up most of the universe's mass and energy. By studying how galaxies and clusters are distributed, astronomers can learn about the properties of dark matter, the behavior of gravity on large scales, and the rate of cosmic expansion. Large surveys, such as the Sloan Digital Sky Survey, (SES), and the Dark Energy Survey, have mapped the cosmic web in unprecedented detail, providing a cosmic map of matter's distribution. The cosmic web also has implications for galaxy formation and evolution. Galaxies located in dense regions, such as clusters, tend to be older and less active in star formation than those in less dense, filamentary regions. This relationship between a galaxy's environment and its properties, known as the galaxy-environment relation, shows how large-scale structures influence the evolution of galaxies. Galaxies in clusters can be affected by gravitational interactions, stripping of gas, and other processes that shape their development. The study of the cosmic web reveals the interconnectedness of the universe, where galaxies are not isolated but part of a larger dynamic structure. The cosmic web is a window into the universe's history, showing how matter has evolved over billions of years and how the forces of gravity and dark matter have shaped its architecture. Through the cosmic web, we gain a sense of the vastness of the cosmos and the intricate patterns that define the universe on the grandest scales. Dark flow, the mysterious motion of galaxy clusters. Dark flow is a mysterious phenomenon observed in the motion of galaxy clusters, suggesting that they are moving in a specific direction at a speed that cannot be explained by the standard model of cosmology. Discovered by analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, MAP, dark flow points to an unknown force or structure beyond the observable universe that appears to be pulling galaxy clusters toward it. This enigmatic motion has sparked debates and investigations into the nature of the universe and the limits of our observational horizon. The concept of dark flow challenges our understanding of cosmic expansion. According to the standard model, galaxy clusters should move randomly, influenced by local gravitational interactions and the general expansion of space. However, dark flow implies a coherent, large-scale motion that does not fit within these expectations. Some scientists suggest that dark flow might be caused by gravitational effects from structures beyond the observable universe, such as a massive supervoid or another region with a higher density of matter. Dark flow has implications for the multiverse hypothesis, as it could be evidence of interactions between our universe and neighboring bubble universes. If other universes exist beyond our cosmic horizon, their gravitational effects might be felt within our observable universe, influencing the motion of galaxy clusters. This idea remains speculative but offers an intriguing explanation for the unexplained motion observed in dark flow. Despite initial observations, the existence of dark flow remains a topic of debate. Some follow-up studies have questioned the data and methods used to detect dark flow, while others have supported its validity. Ongoing observations with new instruments, such as the Planck satellite, aim to clarify whether dark flow is a genuine phenomenon or an artifact of data analysis. If dark flow is confirmed, it would be a groundbreaking discovery, challenging our understanding of cosmology and potentially pointing to new physics or even the existence of other universes. It reminds us that the universe is filled with mysteries, some of which lie beyond our observational limits, hinting at structures and forces that we are only beginning to comprehend. The anthropic principle, the universe fine-tuned for life. The anthropic principle is a philosophical and scientific concept that explores why the universe's fundamental constants appear to be fine-tuned for life. From the strength of gravity to the charge of the electron, the constants of nature fall within narrow ranges that allow for the formation of stars, planets, and the complex chemistry required for life. If these constants were even slightly different, the universe might be a vastly different place, potentially devoid of life as we know it. The anthropic principle comes in two main forms, the weak anthropic principle and the strong anthropic principle. The weak anthropic principle simply states that we observe the universe to be life-friendly, because we are here to observe it. In other words, if the universe were not conducive to life, we would not be here to notice it. The strong anthropic principle, however, suggests that the universe's laws and constants are somehow set in such a way as to allow for the existence of life, raising deeper questions about the purpose and design of the cosmos. The fine-tuning of the universe has led to various interpretations. Some scientists propose that the universe's apparent fine-tuning is a result of chance, while others suggest the existence of a multiverse, where different universes have different physical laws. In this view, we inhabit one of many universes, each with its own constants, and our universe happens to be one where conditions are suitable for life. The anthropic principle raises profound philosophical and scientific questions about the nature of existence. Are the constants of nature arbitrary? Or do they reflect a deeper structure that we have yet to understand? If we are one of many possible universes, what does that mean for our sense of uniqueness? The anthropic principle challenges us to consider our place in the cosmos, suggesting that life may be an integral part of the universe, or a rare accident in a vast multiverse. While the anthropic principle does not offer definitive answers, it provides a framework for exploring one of humanity's oldest questions. Why are we here? By examining the conditions that make life possible, we deepen our understanding of the universe's fundamental nature and reflect on the extraordinary chain of events that led to our existence. White dwarfs and the end of stellar evolution. White dwarfs are the remnants of stars that were once similar to our Sun but have exhausted their nuclear fuel. After a star depletes the hydrogen in its core, it goes through a red giant phase, expanding and shedding its outer layers. What remains is the core, a dense, hot remnant called a white dwarf. These stellar remnants are incredibly compact, with a mass close to that of the Sun but squeezed into a volume about the size of Earth. White dwarfs are sustained by a unique form of pressure called electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed further. This degeneracy pressure balances against the gravitational pull inward, preventing the white dwarf from collapsing. However, if a white dwarf accumulates enough additional mass, typically through interactions in a binary star system, it can reach a critical limit, known as the Chandrasekhar limit. Surpassing this limit leads to a type Iowa supernova, a powerful explosion that completely disrupts the white dwarf. As white dwarfs cool over billions of years, they gradually fade, emitting less and less light. Eventually, they will cool to the point where they no longer emit significant heat or light, becoming black dwarfs. However, this process takes longer than the current age of the universe, so no black dwarfs are thought to exist yet. The final fate of white dwarfs, along with other end-state stars, reflects the eventual quieting of stellar activity as the universe continues to age. White dwarfs are valuable tools in astrophysics for several reasons. They serve as cosmic clocks since their cooling rate provides a measure of time. By studying the temperatures of white dwarfs, astronomers can estimate the age of certain star clusters, helping to refine the timeline of cosmic evolution. White dwarfs also play a crucial role in the study of planetary systems, as remnants of planetary material can sometimes be detected in their atmospheres, providing clues about the fate of planets orbiting dying stars. These stellar remnants serve as reminders of the finite nature of stars and the slow transformation of the universe's luminous matter into dark, cold remnants. The study of white dwarfs not only reveals the life cycles of stars but also hints at the future of the cosmos as it slowly dims over trillions of years. The Kuiper Belt and the edge of our solar system. Beyond the orbit of Neptune lies the Kuiper Belt, a vast region filled with icy objects, dwarf planets, and remnants from the early solar system. This region, which stretches from about 30 to 55 astronomical units from the Sun, is home to Pluto, Haumea, Makemake, and hundreds of thousands of smaller bodies. The Kuiper Belt is thought to be a remnant of the primordial disk of gas and dust that formed the planets, making it a valuable repository of clues about the solar system's origins. Objects in the Kuiper Belt are composed primarily of ice, rock, and organic compounds. These icy bodies are remnants of the early solar system, preserved in the cold outer reaches of space. The composition of Kuiper Belt objects, KBOs, provides insights into the materials and conditions present in the early solar system, as well as the processes that led to planet formation. KBOs are often compared to comets, as they contain similar materials that are mostly unchanged since the solar system's formation. The discovery of the Kuiper Belt in the 1990s significantly changed our understanding of the solar system's structure. It provided the context for the reclassification of Pluto as a dwarf planet, as astronomers recognized that Pluto was just one of many large objects in this distant region. The Kuiper Belt also shed light on the origin of short-period comets, which originate in this region before being perturbed into orbits that bring them closer to the Sun. One of the most fascinating aspects of the Kuiper Belt is the search for a potential ninth planet, often referred to as Planet 9. Evidence for this planet comes from the unusual orbits of some KBOs, which suggest that a large, unseen planet may be exerting a gravitational influence on these distant objects. If Planet 9 exists, it would be a massive planet, perhaps 5 to 10 times the mass of Earth, located far beyond the Kuiper Belt. The Kuiper Belt represents the boundary of our solar system's influence, where the Sun's gravitational pull begins to weaken. Beyond the Kuiper Belt lies the scattered disk and the Oort cloud, a hypothesized shell of icy objects that marks the true outer boundary of the solar system. Exploring the Kuiper Belt gives us a deeper understanding of our cosmic neighborhood, revealing the diversity and complexity of objects orbiting our Sun. The cosmic microwave background's cold spot, evidence of the multiverse. The cosmic microwave background (CMB) is the afterglow of the Big Bang, a faint radiation that fills the universe. While the CMB is remarkably uniform, tiny temperature variations reflect differences in density in the early universe. However, one anomaly stands out, a region known as the cold spot. This region is slightly cooler than expected, and its existence has led to speculation that it may be evidence of a collision between our universe and another bubble universe in a larger multiverse. The cold spot was first identified by the Wilkinson Microwave Anisotropy Probe, MAP, and later confirmed by the Planck satellite. This unusual region is about 1.8 billion light-years across, located in the constellation Eridanus. While it is possible that the cold spot is simply a statistical fluke or a large cosmic void with fewer galaxies, some scientists propose that it may be a signature of a cosmic bruising effect, where our universe interacted with another universe early in its history. If the cold spot were caused by a multiverse interaction, it would provide one of the first pieces of observational evidence supporting the multiverse theory. This idea suggests that our universe is one of many bubbles in a vast, possibly infinite multiverse, each with its own physical laws and constants. While the multiverse remains speculative, it offers a potential explanation for the fine-tuning of the universe, as only certain bubbles would have the right conditions for life. Scientists continue to study the cold spot, using advanced simulations and surveys of galaxy distribution to understand its origin. Whether it is a statistical anomaly, a cosmic void, or evidence of a multiverse, the cold spot challenges our understanding of cosmology and the limits of the observable universe. It reminds us that the universe is filled with mysteries, some of which may hint at realities beyond our own. The Great Attractor and the Laniakea Supercluster. Our Milky Way galaxy is part of a vast structure known as the Laniakea Supercluster, a region containing over 100,000 galaxies spanning 500 million light-years. At the center of this supercluster lies the Great Attractor, a gravitational anomaly that is pulling galaxies, including the Milky Way, toward it at tremendous speeds. The Great Attractor remains largely hidden behind a dense region of dust and stars in our galaxy, making it challenging to observe directly. The Great Attractor's gravitational influence has been known since the 1970s, when astronomers observed that galaxies in the local universe are moving toward a common point. This phenomenon, called peculiar velocity, indicates that an unseen mass is exerting a pull on galaxies across a vast region of space. While the exact nature of the Great Attractor is unknown, it is thought to be a dense region of galaxies and dark matter, possibly containing multiple galaxy clusters. The Laniakea Supercluster, mapped in 2014, revealed the full extent of the region dominated by the Great Attractor's influence. Laniakea, which means immense heaven in Hawaiian, spans a network of galaxies connected by gravitational filaments, creating a complex, interconnected structure. This discovery reshaped our understanding of the cosmic web, showing that the Milky Way is part of a much larger supercluster structure, with the Great Attractor as its gravitational center. The Great Attractor is also connected to an even larger structure known as the Shapley supercluster. Some scientists believe that the Shapley supercluster, located beyond Laniakea, may be pulling on the Great Attractor, creating a cosmic tug-of-war between these massive structures. This ongoing motion suggests that galaxies are not simply drifting through space. They are part of a dynamic web of attraction and motion, shaped by massive gravitational forces. The study of the Great Attractor and the Laniakea supercluster reveals the complex, hierarchical nature of the universe. It challenges our understanding of large-scale structures and shows that galaxies are part of a vast cosmic dance, moving along gravitational currents in a network of superclusters and filaments. At the heart of many galaxies, including our own, lies a powerful and mysterious force, a black hole. These cosmic giants are formed when massive stars collapse under their own gravity, creating an area in space where gravity is so strong that not even light can escape. Black holes are like cosmic vacuums, pulling in everything around them and growing larger with each new piece of matter they consume. But what makes black holes truly fascinating is what happens beyond their event horizon, the point of no return. Imagine a place where time slows down, where gravity is so intense that space itself curves and warps. Scientists theorize that the laws of physics as we know them break down beyond this point, leading to a singularity, a point where density becomes infinite. Here, our understanding of reality falters, and questions arise. Does time cease to exist in a black hole? Is there a way to travel through one? Some theories suggest that black holes could be gateways to other universes, wormholes connecting distant points in space-time, or even a passage to a parallel universe. These ideas may sound like science fiction, but they are grounded in cutting-edge physics and mathematical theories. And then there's Sagittarius A, the supermassive black hole at the center of the Milky Way, located about 26,000 light-years from Earth. This monstrous black hole has a mass 4 million times that of our Sun, exerting a gravitational force so strong that it pulls nearby stars into an orbit around it. Scientists have even observed stars accelerating as they approach Sagittarius A, giving us direct evidence of its immense gravitational influence. Recently, astronomers captured an image of the shadow of a black hole in another galaxy, giving humanity its first ever glimpse of what a black hole looks like. This iconic image, showing a dark circle surrounded by a glowing ring of superheated matter, provides a visual representation of an otherwise invisible object. But as remarkable as this image is, it raises even more questions. What happens inside that dark circle? Is there something beyond the singularity? And could black holes hold the answers to some of the universe's greatest mysteries? Dark matter, the invisible force shaping the universe. Look up at the night sky, and everything you see, planets, stars, galaxies, clouds of gas, is only a small fraction of the universe. In fact, around 85% of the matter in the cosmos is something entirely invisible, known as dark matter. This mysterious substance doesn't emit, absorb, or reflect light, making it completely undetectable by conventional telescopes. Yet, we know it's there, as it exerts a gravitational pull that binds galaxies together, influencing the movement of stars and the very structure of the universe. Dark matter is often described as a cosmic glue, but what is it made of? Scientists have been searching for the answer for decades, but dark matter remains elusive. Some theories suggest it could be made of undiscovered particles that interact only through gravity, while others propose that it could be related to alternate dimensions or hidden aspects of the universe. Some physicists even speculate that dark matter could be a new form of matter altogether, governed by unknown forces and particles. Despite the lack of direct evidence, dark matter is essential to our understanding of the cosmos. Without it, galaxies would fly apart, and the universe as we know it wouldn't exist. Researchers have devised ingenious experiments to try and capture a glimpse of dark matter, building detectors deep underground, shielded from cosmic rays, in hopes of catching an interaction. These experiments involve extremely sensitive instruments and enormous patience, as any signal from dark matter would be faint and rare. The Large Hadron Collider, the world's most powerful particle accelerator, is also being used to search for dark matter particles by smashing protons together at incredibly high speeds. The search for dark matter isn't just about understanding what the universe is made of, it's also about uncovering the forces that shaped it from the very beginning. If we could understand dark matter, we might unlock new insights into the Big Bang, the formation of galaxies, and the ultimate fate of the universe. Some scientists even speculate that dark matter could hold the key to discovering whether there are other dimensions beyond the familiar 3 dimensions of space and 1 of time. Dark energy, the force driving the universe's expansion. As if dark matter weren't mysterious enough, there's another invisible force at play in the universe: dark energy. This force is even stranger than dark matter, as it doesn't just hold galaxies together, it actually drives them apart. In the late 1990s, astronomers discovered that the universe is expanding at an accelerating rate, meaning galaxies are moving away from each other faster and faster. This discovery was completely unexpected, as scientists had assumed that the gravitational pull of galaxies on one another would slow down the expansion over time. But instead, something unknown: dark energy is pushing the cosmos apart, overcoming the force of gravity and stretching the fabric of space itself. Dark energy makes up about 68% of the total energy in the universe, making it the dominant force at cosmic scales. But what is it? No one knows for sure. Some theories suggest it could be related to the vacuum energy of empty space, a type of energy predicted by quantum mechanics. Others propose that it might be an unknown field or force that permeates the universe, something as fundamental as gravity or electromagnetism. The implications of dark energy are profound. If the universe continues to expand at an accelerating rate, it could eventually reach a state where galaxies are so far apart that they're no longer visible to one another. Over trillions of years, stars would burn out and black holes would evaporate, leaving a dark, empty universe. This scenario is known as the Big Freeze, and it represents one possible fate of the cosmos. Yet dark energy remains one of the greatest mysteries in science. Despite its impact on the universe, we have yet to detect it directly or understand its origin. The study of dark energy is an ongoing field of research, with scientists using powerful telescopes to observe distant supernovae and galaxy clusters in an attempt to measure its effects. As we learn more about dark energy, we may come to a deeper understanding of the universe's future, and perhaps even unlock clues about its beginning. Black holes, the guardians and enigmas of the universe. When we speak of black holes, we're referring to some of the most intense and perplexing objects in the universe. These cosmic giants arise from the death of massive stars, which collapse under their own gravity after exhausting their nuclear fuel. The resulting black hole becomes a region of space where gravity is so powerful that it warps the fabric of space-time to an extreme degree. What makes black holes so fascinating is that they challenge our understanding of physics. Inside a black hole lies a point called the singularity, a place where density becomes infinite, and the known laws of physics break down. The singularity, hidden behind the event horizon, holds secrets that could potentially reshape our understanding of gravity, quantum mechanics, and even the origins of the universe itself. Consider the event horizon. It's not a physical boundary, but rather a point of no return. Anything that crosses it, be it matter, light, or radiation, becomes trapped by the black hole's gravity. Beyond the event horizon, space and time switch roles. Instead of time moving forward, all paths lead to the singularity, as if the very fabric of reality is pulling everything inward. But what might exist beyond the singularity? Some theories suggest that black holes could act as tunnels to other parts of the universe, perhaps even as gateways to parallel realities. This idea, known as a wormhole, has inspired science fiction for decades. Though there's no direct evidence that wormholes exist, they remain a tantalizing possibility, as certain mathematical models imply that they could form under specific conditions. If a black hole were indeed a wormhole, it could provide a shortcut across the vast expanses of space, a phenomenon that would revolutionize our approach to cosmic travel. Scientists are also studying black holes to understand how they shape galaxies. At the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. Sagittarius A, the black hole at the heart of the Milky Way, has a mass of over 4 million suns, and its gravitational influence shapes the orbits of stars around it. Some theories even suggest that supermassive black holes play a role in galaxy formation, acting as anchors that pull together gas, dust, and stars to create the spiral, elliptical, and irregular shapes we see in the universe. Yet, as much as we've learned about black holes, they remain shrouded in mystery. Scientists are currently exploring the phenomenon of Hawking radiation, a theoretical process proposed by physicist Stephen Hawking. According to this theory, black holes are not completely black. They emit faint radiation as particles escape from just beyond the event horizon. Over trillions of years, this radiation could cause black holes to slowly evaporate. If this theory is correct, it suggests that even the most powerful objects in the universe are not eternal and may one day vanish entirely. The study of black holes is ongoing, with advanced telescopes and observatories capturing new data all the time. In 2019, humanity achieved a major milestone with the first ever image of a black hole captured by the Event Horizon Telescope. This image showed a glowing ring surrounding a dark center, the shadow of a black hole in the galaxy M87. This image provides us with a visual representation of a phenomenon once thought to be purely theoretical and offers new insights into the nature of gravity and matter under extreme conditions. As we continue to study black holes, we move closer to unlocking their secrets. They serve as reminders of the universe's power, mystery, and complexity, a symbol of the endless questions that await us in the cosmos. Dark matter, the hidden scaffold of the universe. The discovery of dark matter revolutionized our understanding of the cosmos. In the 1930s, Swiss astronomer Fritz Zwicky observed that galaxies within clusters moved at speeds that couldn't be explained by visible matter alone. There had to be some unseen substance providing additional mass and gravitational pull, holding these galaxies together. This discovery led to the theory of dark matter, a substance that makes up about 85% of all matter in the universe, yet remains completely invisible. Dark matter doesn't interact with electromagnetic forces, meaning it neither emits nor absorbs light. Its presence is known only through its gravitational effects, which influence the motion of galaxies, the shape of galactic clusters, and the bending of light from distant stars. Without dark matter, galaxies would lack the mass needed to hold themselves together, and the universe as we know it would not exist. But what exactly is dark matter? Scientists have been searching for answers for decades, yet it remains one of the greatest mysteries in astrophysics. Some theories propose that dark matter consists of WIMPs, or weakly interacting massive particles, which would be detectable only through gravity and not through other fundamental forces. Other hypotheses suggest XIANs, hypothetical particles that could account for dark matter's strange properties. Detecting dark matter has become one of the primary goals of modern physics. To do so, researchers have built sensitive detectors in underground laboratories, shielded from cosmic rays and other sources of interference. These detectors are designed to capture rare interactions between dark matter particles and ordinary matter. However, after years of experimentation, scientists have yet to detect a single dark matter particle. Dark matter also raises questions about the structure and evolution of the universe. It is thought to form a cosmic web, a vast network of dark matter filaments that stretch across the cosmos, connecting galaxies and clusters. This web-like structure provides the scaffolding upon which galaxies and stars form, guiding the distribution of matter in the universe. Computer simulations show that, without dark matter, the universe would be far less structured, lacking the vast networks and clusters we observe. In addition to particle detectors, scientists are using powerful telescopes to map the effects of dark matter on distant galaxies. Gravitational lensing, a phenomenon where light from a distant object is bent by the gravity of a massive object between it and the observer, provides indirect evidence of dark matter. When astronomers observe galaxy clusters, they often find that the light from background galaxies is distorted more than expected, suggesting the presence of dark matter in these regions. The existence of dark matter has led to questions about whether our understanding of gravity is complete. Some physicists have proposed alternative theories, such as modified Newtonian dynamics, MOND, which suggests that gravity itself might behave differently on cosmic scales. While these theories remain controversial, they reflect the ongoing search for a deeper understanding of dark matter and its role in the universe. Ultimately, dark matter is more than just a scientific puzzle. It's a reminder that the universe is full of unseen wonders, forces, and particles that challenge our perception of reality. As scientists continue to explore this invisible world, they bring us closer to understanding the true nature of the cosmos. Dark energy, the mysterious force driving cosmic expansion. Just when scientists thought they had a handle on the universe's composition, a groundbreaking discovery in the late 1990s revealed an even deeper mystery: dark energy. By observing distant supernovae, astronomers found that the universe's expansion was accelerating, a surprising result, as it was previously believed that gravity would gradually slow down this expansion. This discovery led to the theory of dark energy, a force that makes up about 68% of the universe and appears to be pushing galaxies apart. Dark energy is one of the most perplexing phenomena in astrophysics, as its nature and origin remain entirely unknown. Some theories suggest it could be related to the vacuum energy of space itself, a property predicted by quantum mechanics, where empty space is not truly empty, but filled with virtual particles that pop in and out of existence. This vacuum energy might exert a repulsive force, causing space to expand at an accelerating rate. Other theories propose that dark energy is a new fundamental field, similar to the fields of electromagnetism or gravity, that permeates the entire universe. Known as quintessence, this hypothetical field could vary over time and space, potentially influencing the universe's structure and evolution. If dark energy behaves in this way, it could have profound implications for our understanding of the cosmos. The study of dark energy has led scientists to reconsider the ultimate fate of the universe. If dark energy continues to drive cosmic expansion, the universe could end in what's known as the Big Freeze. In this scenario, galaxies would drift further apart, stars would burn out, and black holes would eventually evaporate, leaving a cold, dark, and empty cosmos. However, some theories suggest other possibilities, such as the Big Rip, where dark energy grows stronger over time, eventually tearing apart galaxies, stars, planets, and even atoms. Despite its impact on the universe, dark energy remains an elusive subject, with no direct way to observe or measure it. Scientists are conducting experiments with telescopes that can measure subtle distortions in space caused by dark energy's effects. Projects like the Dark Energy Survey and the upcoming Euclid mission aim to map the distribution of galaxies across billions of light years, providing clues about how dark energy has shaped the cosmos over time. Understanding dark energy is not just about solving a scientific puzzle, it's about uncovering the forces that govern the universe. If we can unlock the secrets of dark energy, we may gain insight into the fundamental nature of reality, the structure of space-time, and the ultimate destiny of the cosmos. Black holes. Beyond the event horizon, into the unknown. Black holes are among the most mysterious and awe-inspiring phenomena in the universe. These celestial giants form when massive stars exhaust their fuel and collapse under their own gravity, condensing into a point of infinite density known as a singularity. At this point, the gravitational pull is so strong that not even light can escape, rendering the black hole invisible to our eyes. But what truly lies within these cosmic enigmas? And how do they impact the very fabric of space-time? Imagine standing near the event horizon of a black hole. This boundary is a one-way gate into the unknown. Anything that crosses it is forever trapped by the black hole's gravity. Time itself slows to a crawl as you approach, and the laws of physics as we know them begin to break down. If you watched someone fall toward a black hole, they would appear to slow down and freeze in time, lingering on the edge of the event horizon as light itself struggles to escape the intense gravity. The singularity at the core of a black hole represents one of the greatest challenges to our understanding of the universe. At this point, space and time curve infinitely, and our current theories of physics cannot accurately describe what happens. Some scientists propose that singularities could be windows into alternate realities or other dimensions, leading to concepts such as wormholes, hypothetical tunnels through space-time that might connect distant regions of the cosmos or even separate universes entirely. Physicists like Stephen Hawking have explored the idea that black holes are not entirely black. According to his theory, black holes emit a faint radiation, now known as Hawking radiation, caused by quantum effects near the event horizon. Over unimaginable timescales, this radiation could cause black holes to lose mass and eventually evaporate completely. If true, this process would mean that black holes are not eternal and may eventually disappear from the cosmos. The sheer size and power of black holes can be mind-boggling. The largest known black holes, called supermassive black holes, reside at the centers of galaxies. Sagittarius A, the black hole at the heart of the Milky Way, has a mass over 4 million times that of our Sun. Some supermassive black holes reach billions of solar masses, exerting a gravitational influence so profound that they shape the structure of entire galaxies around them. These cosmic behemoths are thought to play a central role in galaxy formation, acting as gravitational anchors that draw in gas, dust, and stars, ultimately shaping the galaxy's spiral arms and core. The study of black holes is not only a journey into the extremes of physics, but also a window into the nature of reality itself. When the Event Horizon Telescope captured the first image of a black hole in 2019, it offered humanity a glimpse of the unseeable, a dark shadow surrounded by a glowing ring of light, representing matter heated to incredible temperatures as it spirals toward oblivion. This image was a triumph of technology and collaboration, made possible by a network of telescopes around the world working in unison to capture something that had previously been purely theoretical. Our fascination with black holes extends beyond science. They are symbols of mystery, destruction, and creation, embodying the duality of the universe itself. They are both a beginning and an end, a place where matter is torn apart yet possibly reborn in ways we cannot yet comprehend. In the coming decades, scientists hope to unlock more secrets of black holes using advanced observatories, gravitational wave detectors, and even hypothetical space probes that might one day venture close enough to study these enigmatic objects up close. Each new discovery about black holes brings us closer to answering some of the universe's biggest questions. What lies beyond the event horizon? Is there a way to traverse these cosmic giants safely? Could they be used as portals to other parts of space and time? The answers remain elusive, but one thing is certain: black holes are reminders of the vast, unexplored frontiers of the cosmos, where the known laws of physics collide with the unknown, beckoning us to venture deeper into the heart of the universe. Dark matter, the cosmic glue holding the universe together. Dark matter, an unseen substance that pervades the cosmos, is one of the most significant mysteries in modern physics. Despite being invisible, dark matter makes up about 85% of the matter in the universe, playing a crucial role in shaping galaxies, clusters, and the very structure of the cosmos itself. But what is dark matter, and how do we know it's there if we can't see or touch it? The existence of dark matter was first inferred in the 1930s by astronomer Fritz Zwicky, who noticed that galaxies in clusters were moving much faster than their visible mass could account for. There had to be some hidden mass providing additional gravitational pull to keep these galaxies bound together. Decades later, further evidence emerged from the study of galactic rotation curves. Stars at the outer edges of galaxies were moving just as fast as those closer to the center, defying expectations based on visible matter alone. The term dark matter is somewhat misleading, as it implies an absence of light. However, dark matter doesn't interact with light or other electromagnetic radiation at all, making it completely invisible to telescopes and other traditional observational methods. Instead, we detect dark matter only through its gravitational effects on visible matter. This mysterious substance acts as a kind of cosmic glue, providing the gravitational binding force that holds galaxies together and influences the movement of stars within them. Physicists have proposed several possible candidates for dark matter, including WIMP, weakly interacting massive particles, which would interact only through gravity and possibly the weak nuclear force, making them extremely difficult to detect. Another candidate is the action, a hypothetical particle that could account for the gravitational effects we observe without interacting with regular matter. Despite decades of research, however, dark matter remains elusive, with no direct detection yet achieved. To search for dark matter, scientists have constructed ultra-sensitive detectors deep underground, shielded from cosmic rays and other sources of interference. These detectors are designed to capture the rare interactions between dark matter particles and ordinary matter, should they occur. The Large Hadron Collider, the world's most powerful particle accelerator, is also being used to search for signs of dark matter, as it collides protons at nearly the speed of light, creating conditions similar to those of the early universe. Dark matter is not just a local phenomenon, it forms a vast, interconnected web that spans the cosmos. This cosmic web is composed of dark matter filaments, which act as scaffolding for the formation of galaxies and clusters. Galaxies are not randomly distributed in the universe. Instead, they form along these dark matter filaments, with vast cosmic voids in between. The structure of the cosmic web has been observed through computer simulations and indirectly confirmed through gravitational lensing, where light from distant galaxies is bent by the gravitational influence of dark matter. Gravitational lensing is a powerful tool for studying dark matter, as it reveals the distribution of mass in galaxy clusters and provides evidence of dark matter's presence. When light from a distant galaxy passes through a cluster on its way to Earth, it is bent by the cluster's gravity, creating a lensing effect. This bending of light allows astronomers to map the mass of the cluster, including the dark matter, providing a glimpse into its distribution across space. The nature of dark matter remains one of the biggest unanswered questions in science. Some physicists believe that solving the mystery of dark matter could lead to a new understanding of gravity, or even uncover hidden dimensions of reality. Others suggest that dark matter may be the key to understanding the Big Bang, galaxy formation, and the eventual fate of the universe. Whatever the true nature of dark matter, it is clear that it plays a fundamental role in the structure and evolution of the cosmos. The search for dark matter is more than a scientific pursuit. It's a quest to understand the hidden forces that shape our universe. It's a reminder that the universe is full of unseen wonders, mysteries that defy our current understanding and challenge us to look beyond the visible. As we continue to explore this invisible world, we may one day unlock secrets that reveal a new layer of reality, a deeper understanding of the forces that govern existence itself. Dark energy, the force pulling the universe apart. Dark energy is perhaps even more mysterious than dark matter, representing an unknown force that drives the accelerated expansion of the universe. While dark matter holds galaxies together, dark energy works in the opposite direction, pushing galaxies apart and causing the universe to expand at an ever-increasing rate. Together, dark matter and dark energy make up roughly 95% of the total energy and matter in the universe, yet we know almost nothing about either. The existence of dark energy was discovered in the late 1990s, when astronomers observed distant supernovae and found that the universe's expansion was accelerating, not slowing down as previously expected. This discovery was a shock to the scientific community, as it implied that a new force, dark energy, was at work, overcoming the gravitational pull of galaxies and causing the universe to expand faster over time. Dark energy is often associated with the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Originally, Einstein included this constant to allow for a static universe, but he later discarded it, calling it his biggest blunder after the discovery of cosmic expansion. However, the discovery of dark energy has revived interest in the cosmological constant, suggesting that it might indeed be a real force. Some theories propose that dark energy could be a property of space itself, with a vacuum energy that exerts a repulsive force. Quantum mechanics predicts that empty space is not truly empty, but filled with virtual particles that pop in and out of existence. This vacuum energy could create a pressure that drives the expansion of the universe, though the exact mechanisms remain unknown. The implications of dark energy extend to the ultimate fate of the universe. If dark energy continues to drive expansion, galaxies will drift further and further apart, eventually leaving each galaxy isolated in a vast, empty void. This scenario, known as the Big Freeze, suggests a dark, cold end for the cosmos, where stars burn out and black holes eventually evaporate, leaving a dark, lifeless universe. The Big Bang, the birth of the cosmos and the beginning of time. The story of the universe begins with the Big Bang, a moment that transformed pure energy into matter and set in motion the cosmic clock that defines our understanding of time and space. Roughly 13.8 billion years ago, everything we know, the stars, planets, galaxies, and even time itself, emerged from a singular point of infinite density and temperature. This singularity contained all the energy that would eventually form everything we see today. At the moment of the Big Bang, the universe expanded at an incredible rate, a process known as inflation. In less than a trillionth of a second, the universe grew from a subatomic scale to a size larger than a galaxy, creating space, time, and the fundamental particles that would form matter. Inflation remains one of the most mysterious phases of the universe's history, as it defies our conventional understanding of physics. During this brief moment, space itself stretched faster than the speed of light, a process that left an imprint on the structure of the cosmos that we can still observe today. As the universe expanded and cooled, fundamental forces and particles began to take shape. Protons, neutrons, and electrons formed, eventually giving rise to hydrogen and helium, the building blocks of stars. About 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons, forming neutral atoms. This process, known as recombination, allowed light to travel freely for the first time, creating what we now observe as the cosmic microwave background, CMB. Radiation, a faint glow that fills the universe and provides a snapshot of the cosmos in its infancy. The CMB is often described as the afterglow of the Big Bang, a relic of the early universe that allows scientists to peer back in time. By studying variations in the CMB, scientists have gained insights into the density, temperature, and composition of the early universe. These variations, or anisotropies, are tiny fluctuations that eventually led to the formation of galaxies and clusters, shaping the universe we see today. The study of the Big Bang raises profound questions about the nature of reality. What existed before the Big Bang? Is our universe just one of many in a vast multiverse? Some theories suggest that the Big Bang may have been a transition from one cosmic state to another, a kind of bounce from a previous universe. Others propose that our universe is part of a larger multiverse, where countless other universes with different physical laws may exist. While these ideas are speculative, they challenge us to think beyond the boundaries of our universe and consider the possibility of realms beyond our own. As we continue to study the Big Bang, we come closer to understanding the origins of existence itself. New experiments and telescopes, such as the James Webb Space Telescope, are designed to look back in time to when the first stars and galaxies formed, providing insights into the early stages of the universe. Each discovery brings us one step closer to answering the ultimate question: how did everything begin? The life cycle of stars, from birth to supernova. Stars are the cosmic forges of the universe, responsible for creating the elements that make up planets, life, and everything we see. The life of a star begins in vast clouds of gas and dust known as nebulae. These stellar nurseries are filled with hydrogen and helium, the lightest elements left over from the Big Bang. Over millions of years, gravity pulls clumps of gas and dust together, forming dense regions that eventually collapse under their own weight. As a protostar forms, it heats up, and when the temperature and pressure at its core reach a critical point, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing tremendous energy in the process. This energy counteracts the force of gravity, creating a delicate balance that allows the star to shine. A star will spend most of its life in this stable phase, known as the main sequence, burning hydrogen into helium and radiating light and heat. The size of a star determines its life cycle and eventual fate. Smaller stars, like red dwarfs, burn their fuel slowly and can live for trillions of years. Our Sun, a medium-sized star, has a lifespan of about 10 billion years and is currently in its middle age. When it exhausts its hydrogen fuel, the Sun will expand into a red giant, engulfing the inner planets, including Earth. In this stage, the Sun will shed its outer layers, creating a beautiful nebula, while its core will collapse into a dense white dwarf, a stellar remnant that will gradually cool over billions of years. Massive stars, however, live fast and die young. These stars burn through their fuel quickly, fusing heavier elements like carbon, oxygen, and eventually iron. Iron fusion does not release energy. Instead, it absorbs it, causing the core to collapse. This catastrophic collapse triggers a supernova, a powerful explosion that releases more energy in a few seconds than our Sun will emit in its entire lifetime. Supernovae are not just destructive events, they are also creative forces. The intense heat and pressure of a supernova forge elements heavier than iron, such as gold, platinum, and uranium, which are then scattered across the cosmos. These elements become part of new stars, planets, and even life itself. In this way, supernovae play a crucial role in cosmic evolution, seeding the universe with the building blocks of life. The remnants of massive stars can take on extraordinary forms. If the core left after a supernova is massive enough, it will collapse into a neutron star, a dense object composed almost entirely of neutrons, with a mass greater than the Sun but a diameter of only about 20 kilometers. Neutron stars have incredibly strong magnetic fields and can emit beams of radiation as they spin, becoming pulsars. In some cases, the core may collapse further, forming a black hole, where gravity is so strong that not even light can escape. The life cycle of stars is a reminder of the cyclical nature of the cosmos. Stars are born, live, and die, creating and recycling the elements that make up the universe. Our own Sun, for example, is a third-generation star, meaning it contains elements forged in previous generations of stars. In this sense, every atom in our bodies was once part of a star, a cosmic connection that binds us to the universe in a profound way. Galaxies, the cosmic cities of stars. Galaxies are vast collections of stars, gas, dust, and dark matter, bound together by gravity and spread across the cosmos like cosmic cities. The Milky Way, our home galaxy, contains hundreds of billions of stars, along with nebulae, star clusters, and countless planetary systems. But the Milky Way is just one of an estimated 2 trillion galaxies in the observable universe, each with its own unique structure and history. Galaxies come in various shapes and sizes, with the most common types being spiral, elliptical, and irregular. Spiral galaxies, like the Milky Way and Andromeda, have a flat, rotating disk with arms that spiral outward, containing young, bright stars and nebulae. The center of a spiral galaxy, known as the bulge, contains older stars and is often home to a supermassive black hole. Elliptical galaxies, on the other hand, are more spherical or oval-shaped and lack the distinct structure of spiral arms. These galaxies contain older stars and very little gas or dust, suggesting that they have completed their star formation processes. Irregular galaxies, as their name implies, have no defined shape. They are often small and contain a mix of young and old stars. Some irregular galaxies may have once been spiral or elliptical, but interactions with other galaxies have distorted their structure. Galaxy collisions and mergers are common in the cosmos, as gravity draws galaxies toward one another over billions of years. When galaxies collide, their stars rarely come into direct contact, but the gravitational interactions trigger waves of star formation and can reshape the galaxies into new forms. Our closest galactic neighbor, Andromeda, is on a collision course with the Milky Way. In about 4.5 billion years, the two galaxies will merge in a spectacular cosmic dance, creating a new, larger galaxy often referred to as Milkomeda. This merger will likely disrupt the orbits of stars and planetary systems, though our Sun and solar system may survive the encounter. The collision of galaxies is a slow process, taking millions of years, but it represents the dynamic, ever-changing nature of the universe. Galaxies are not isolated entities. They are part of larger structures known as galaxy clusters and superclusters. The Milky Way, for example, is part of the Local Group, a cluster of about 54 galaxies that includes Andromeda and the Triangulum galaxy. The Local Group, in turn, is part of the Laniakea supercluster, a vast network of galaxies stretching over 500 million light-years. These clusters and superclusters form a web-like structure across the cosmos, with filaments of galaxies and vast cosmic voids in between. The study of galaxies provides insights into the history and evolution of the universe. By observing distant galaxies, astronomers can look back in time, as the light from these galaxies has traveled for billions of years to reach us. This allows scientists to study how galaxies formed and evolved over cosmic time. Early galaxies were smaller and more chaotic than modern galaxies, gradually growing through mergers and accretion to become the massive structures we see today. Each galaxy tells a story of cosmic evolution, a tale of star formation, interactions, and transformation. In many ways, galaxies are like living entities, constantly changing, merging, and evolving. Our galaxy, the Milky Way, has undergone multiple mergers with smaller galaxies in its past, and remnants of these galaxies can still be seen in the form of star streams that orbit the galactic halo. This process of galactic evolution continues. As new stars are born, old stars die, and galaxies grow and change over billions of years. Quasars, beacons of light from the early universe. Quasars are among the brightest and most energetic objects in the universe, outshining entire galaxies despite being only a few light years across. These distant beacons are powered by supermassive black holes at the centers of young galaxies, where gas and dust spiral inward, forming an accretion disk around the black hole. As this material heats up to millions of degrees, it emits an incredible amount of light, creating a quasar that can be seen billions of light years away. The discovery of quasars in the 1960s revealed a new layer of cosmic history. At the time, astronomers observed strange points of light that looked like stars but emitted radio waves far stronger than any known star. Spectroscopic analysis showed that these objects were extremely distant, and yet they were visible from Earth, meaning they must be emitting massive amounts of energy. Scientists now know that quasars are the luminous cores of young, active galaxies in the early universe, fueled by the intense gravitational forces of their central black holes. Quasars are more than just brilliant lights in the cosmos, they are windows into the past. Because they are so distant, the light we see from quasars began its journey billions of years ago, providing a glimpse into the conditions of the early universe. Some quasars date back to only a few 100 million years after the Big Bang, making them invaluable tools for studying the formation and evolution of galaxies. These early quasars help scientists understand how supermassive black holes formed and grew in the young universe, shedding light on a time when galaxies were still in their infancy. The energy output of a quasar is staggering. A typical quasar can emit hundreds of times the energy of the Milky Way, despite being only a fraction of its size. This energy is released across the electromagnetic spectrum, from radio waves to X-rays, and it affects the surrounding galaxy in profound ways. The radiation from a quasar can heat the gas in its host galaxy, slowing down or even halting star formation. This process, known as quasar feedback, is thought to play a critical role in galaxy evolution, regulating the growth of galaxies by limiting the amount of gas available for new stars. Quasars also provide insights into the distribution of matter in the universe. As the light from a quasar travels across billions of light years, it passes through intergalactic gas clouds and distant galaxies, leaving absorption lines in the quasar's spectrum. By studying these absorption lines, astronomers can map the distribution of hydrogen, metals, and other elements in the early universe, revealing the structure of the cosmic web and the formation of large-scale structures. Although quasars are rare in the present-day universe, they were much more common in the early cosmos. Over billions of years, most quasars have quieted down as their central black holes have consumed or dispersed the surrounding gas and dust. The Milky Way's central black hole, Sagittarius A, may have once been a quasar, but it is now dormant, only occasionally flaring as it consumes small amounts of material. The study of quasars not only illuminates the nature of black holes and galaxy formation, but also tells the story of a young, active universe, filled with dynamic forces and brilliant lights. Pulsars and neutron stars, the remnants of exploded stars. When massive stars reach the end of their lives, they often explode in spectacular supernovae, leaving behind dense remnants known as neutron stars. These remnants are incredibly compact, packing more mass than the Sun into a sphere only about 20 kilometers in diameter. A neutron star's density is so extreme that a single teaspoon of its material would weigh about 1 billion tons on Earth. Neutron stars are primarily composed of neutrons, particles that result from the fusion of protons and electrons under immense gravitational pressure. In a neutron star, atoms are crushed so tightly that even their constituent particles lose their individual identities, creating a state of matter unlike anything found on Earth. The core of a neutron star is a realm of extreme physics, where quantum mechanics and gravity interact in ways that challenge our understanding of matter. Some neutron stars become pulsars, spinning rapidly and emitting beams of electromagnetic radiation from their magnetic poles. As the pulsar rotates, these beams sweep across space, creating a lighthouse effect that makes the pulsar appear to pulse on and off. Pulsars can rotate incredibly fast, with some spinning hundreds of times per second. These millisecond pulsars are among the most precise clocks in the universe, with a regularity so consistent that scientists use them to test the nature of space-time and detect gravitational waves. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, who observed a regular pattern of radio pulses coming from a distant source. Initially dubbed LGM for Little Green Men, the signals turned out to be natural, marking the first detection of a pulsar. This discovery opened a new field of astrophysics, revealing a previously hidden population of neutron stars and providing new insights into the life cycles of stars. Neutron stars and pulsars offer a unique window into extreme states of matter. Scientists believe that the core of a neutron star may contain exotic forms of matter, such as quark-gluon plasma, where quarks, the fundamental building blocks of protons and neutrons, exist freely, unbound by the usual forces. Studying neutron stars could help physicists understand these exotic states and test theories that go beyond the standard model of particle physics. In recent years, astronomers have observed strange phenomena from certain neutron stars known as magnetars. These neutron stars have extraordinarily strong magnetic fields, up to 1,000 trillion times stronger than Earth's magnetic field. Magnetars occasionally release bursts of X-rays and gamma rays, likely due to stargaze caused by the shifting of the neutron star's crust. These bursts are so powerful that they can disrupt Earth's atmosphere from thousands of light years away, despite originating from an object only a few kilometers across. Pulsars, neutron stars, and magnetars are not only fascinating objects but also valuable tools for studying the universe. By observing the timing of pulsar signals, scientists have detected ripples in space-time known as gravitational waves. The precise timing of pulsar signals can also help astronomers map the interstellar medium, the thin soup of gas and dust that fills the space between stars. These stellar remnants serve as cosmic laboratories, allowing scientists to study physics under conditions that cannot be replicated on Earth. Cosmic rays, high-energy particles from the depths of space. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, originating from sources both within and beyond our galaxy. These particles, primarily protons, strike Earth's atmosphere with tremendous energy, creating showers of secondary particles that cascade down to the surface. While most cosmic rays are harmless, some possess energies millions of times greater than anything produced in human-made accelerators, presenting a puzzle for scientists. The origin of cosmic rays is one of the great mysteries of astrophysics. Many cosmic rays are thought to originate from supernovae, where the shock waves generated by stellar explosions accelerate particles to high speeds. However, the most energetic cosmic rays, known as ultra-high-energy cosmic rays, appear to come from distant sources outside the Milky Way, possibly active galactic nuclei, quasars, or even more exotic phenomena. Understanding the origin of these particles could provide insights into some of the most energetic processes in the universe. When cosmic rays collide with atoms in Earth's atmosphere, they create a shower of secondary particles, including muons, neutrinos, and gamma rays. These particles are detected by specialized observatories on Earth, such as the Pierre Auger Observatory in Argentina and the IceCube Neutrino Observatory in Antarctica. By studying the properties of cosmic rays, scientists hope to unlock secrets about their sources and the processes that accelerate them to such high energies. Cosmic rays also pose challenges for space exploration. High-energy particles can damage spacecraft electronics and pose a health risk to astronauts. As humanity ventures further into space, understanding and mitigating the effects of cosmic rays will be crucial for long-duration missions to the Moon, Mars, and beyond. Researchers are developing shielding materials and other protective measures to safeguard astronauts from cosmic radiation, but the challenge remains significant. In addition to their astrophysical significance, cosmic rays have practical applications here on Earth. They are used in a technique called muon tomography, which allows scientists to see through dense materials. By measuring the absorption of cosmic ray muons, researchers can create images of the interior of volcanoes, pyramids, and even nuclear reactors. This technique has led to discoveries in archaeology, geology, and engineering, demonstrating the far-reaching impact of cosmic rays beyond the field of astrophysics. Cosmic rays remind us of the dynamic, Energetic universe. We inhabit a universe where high-speed particles travel vast distances, bringing information from distant stars and galaxies. By studying cosmic rays, scientists gain insights into the forces that shape the cosmos. From the life cycles of stars to the violent process at the hearts of galaxies. These particles, though invisible to the naked eye, connect us to distant corners of the universe, bridging the gap between Earth and the farthest reaches of space. Gravitational waves, ripples in the fabric of space-time. Gravitational waves are disturbances in the very fabric of space-time, created by massive objects undergoing acceleration. First predicted by Albert Einstein's theory of general relativity in 1915, these waves were only directly detected a century later, in 2015, by the Laser Interferometer Gravitational Wave Observatory, LIGO. This landmark discovery confirmed a fundamental aspect of our understanding of gravity and opened a new way to observe the universe, one that doesn't rely on light, but rather on the subtle stretching and compression of space itself. Gravitational waves are produced by cataclysmic events such as the collision of black holes or neutron stars. When these massive objects spiral toward each other and merge, they release an immense amount of energy in the form of gravitational waves, sending ripples across the cosmos at the speed of light. These waves are incredibly faint by the time they reach Earth, with distortions smaller than the width of an atomic nucleus, yet advanced technology allows scientists to detect them and measure their effect. The ability to observe gravitational waves has given astronomers a new tool for exploring the universe. Traditional telescopes rely on light, which can be absorbed, scattered, or blocked by interstellar dust. Gravitational waves, however, travel unimpeded through matter, allowing us to observe events hidden from view by traditional means. For example, the merger of black holes emits no visible light, but the gravitational waves they produce reveal details about their mass, spin, and distance. The study of gravitational waves has profound implications for understanding the nature of space-time, gravity, and the cosmos itself. When two neutron stars collide, they create gravitational waves that carry information about the star's structure, composition, and behavior in extreme gravitational fields. These collisions are also thought to produce heavy elements like gold and platinum, scattering them across the universe. By studying these kilonova events, scientists gain insights into both stellar evolution and the origins of elements on Earth. In addition to binary mergers, gravitational waves could reveal other exotic phenomena, such as the oscillations of black holes, the core collapse of massive stars, or even the faint echoes of the Big Bang itself. Some theories propose that the early universe, during its rapid inflationary phase, might have generated gravitational waves. These primordial gravitational waves would carry information about the universe's birth and the fundamental forces that shaped it. New observatories are being developed to study gravitational waves with even greater sensitivity and precision. The European Space Agency's Laser Interferometer Space Antenna, LISA, is an ambitious mission scheduled for the 2030s that will place 3 spacecraft in orbit around the Sun, forming a giant triangle millions of kilometers wide. LISA will detect lower-frequency gravitational waves produced by supermassive black holes and other massive cosmic phenomena, extending our reach into the gravitational universe. Gravitational waves provide a window into the most extreme environments in the cosmos, offering a new way to study the universe's violent processes and revealing a universe in constant motion. They remind us that space-time itself is dynamic, a flexible medium that responds to the motion of matter and energy. With each new detection, gravitational wave astronomy brings us closer to understanding the unseen forces that shape the cosmos, and challenges us to imagine a universe where even the very fabric of reality ripples and dances in response to cosmic events. Exoplanets, worlds beyond our solar system. Exoplanets, or planets that orbit stars outside our solar system, represent one of the most exciting frontiers in astronomy. Since the first confirmed detection of an exoplanet in 1992, scientists have discovered thousands of these distant worlds, revealing an astonishing diversity of planetary systems. Some exoplanets are similar to Earth, while others defy our expectations, orbiting close to their stars as hot Jupiters or existing in binary star systems. The search for exoplanets is not just about cataloging distant worlds. It's about finding places where life might exist and understanding the conditions that lead to planetary formation. Exoplanets are detected using several techniques, with the transit and radial velocity methods being the most common. The transit method involves observing the dimming of a star's light as a planet passes in front of it, while the radial velocity method detects the slight wobble in a star's motion caused by the gravitational pull of an orbiting planet. These methods have allowed astronomers to detect exoplanets ranging from Earth-sized rocky planets to gas giants, many times the size of Jupiter. One of the most intriguing aspects of exoplanet research is the search for habitable worlds, planets located in the habitable zone of their star, where conditions might allow liquid water to exist. This Goldilocks zone is neither too hot nor too cold, and it's considered a key factor for life as we know it. Several potentially habitable exoplanets have been discovered, including Proxima Centauri b, a planet orbiting the closest star to our solar system, and TRAPPIST-1e, one of 7 Earth-sized planets orbiting a single star. However, the diversity of exoplanets has challenged our assumptions about planetary systems. Some planets orbit so close to their stars that their atmospheres are stripped away by stellar radiation, while others are rogue planets, drifting through space without a parent star. There are also super-Earths, rocky planets larger than Earth but smaller than Neptune, and mini-Neptunes, gas giants that are significantly smaller than Neptune. With the launch of the James Webb Space Telescope, astronomers are beginning to study the atmospheres of exoplanets in unprecedented detail. By analyzing the light that passes through an exoplanet's atmosphere during a transit, scientists can detect chemical signatures of molecules such as water vapor, methane, and carbon dioxide. This technique, known as transmission spectroscopy, could reveal the presence of biosignatures, molecules associated with life. The study of exoplanets raises profound questions about the uniqueness of Earth and the potential for life elsewhere in the universe. If we discover biosignatures on an exoplanet, it would suggest that life is not a rare phenomenon but a common feature of the cosmos. Alternatively, the absence of biosignatures would underscore the preciousness of life on Earth and the delicate conditions that make it possible. Exoplanet research is rapidly advancing, with missions like TESS, Transiting Exoplanet Survey Satellite, and upcoming projects like LUVOIR, Large UV Optical IR Surveyor, and HAPEX Habitable Exoplanet Observatory, designed to search for Earth-like planets around Sun-like stars. These missions could bring us closer to answering one of humanity's oldest questions: are we alone in the universe? Cosmic background radiation, the echo of the Big Bang. Cosmic microwave background, CMB, radiation is a faint glow that permeates the entire universe, an afterglow of the Big Bang that provides a snapshot of the cosmos in its earliest moments. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is considered one of the most important discoveries in cosmology, offering a window into the conditions that existed about 380,000 years after the Big Bang, when the universe first became transparent to light. The CMB is remarkably uniform, with tiny fluctuations in temperature that correspond to regions of slightly different densities in the early universe. These density variations eventually grew into the galaxies and clusters we see today, making the CMB a fossil piece of evidence for understanding cosmic structure. By studying the CMB's temperature variations, scientists have been able to determine the universe's age, composition, and rate of expansion, refining our understanding of the cosmos. One of the most fascinating aspects of the CMB is its pattern of anisotropies, tiny fluctuations in temperature that are only a few millionths of a degree. These anisotropies are imprints of quantum fluctuations from the very beginning of the universe, stretched to cosmic scales during the period of rapid inflation. By studying these patterns, cosmologists can test theories about the early universe and the forces that shaped it. The CMB has also revealed a curious anomaly known as the cold spot, a region of the sky that is cooler than expected. Some scientists believe this could be a statistical fluke, while others suggest it might be evidence of a larger cosmic structure, such as a supervoid. There are even more speculative ideas suggesting that the cold spot could be a sign of interaction with another universe, a tantalizing hint of a multiverse beyond our own. Observations of the CMB have led to the development of the Lambda Cold Dark Matter (LACDIM) model, which describes the universe's composition and evolution. According to this model, the universe is composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. The CMB provides indirect evidence for both dark matter and dark energy, helping scientists understand their role in cosmic expansion and structure formation. The study of the CMB continues to evolve, with new instruments like the Planck satellite providing detailed maps of the CMB's temperature and polarization. Future missions, such as ChemBees-4, aim to measure the CMB with even greater precision, potentially revealing primordial gravitational waves from the universe's inflationary period. These observations could provide direct evidence for inflation, bringing us closer to understanding the origins of space-time. The CMB is a testament to the power of observation and inference, allowing scientists to peer back in time to the dawn of the cosmos. It represents the first light of the universe, a relic of creation that continues to shape our understanding of existence. By studying the CMB, we explore not only the birth of the universe, but also the fundamental forces that govern its evolution, providing a cosmic context for the story of life and matter. The multiverse, beyond the edges of our universe. One of the most mind-bending concepts in modern physics is the idea of the multiverse, the possibility that our universe is just one of countless others. This concept stems from various theories in physics, including string theory, cosmic inflation, and quantum mechanics, each suggesting that there may be realms beyond our own where the laws of physics, dimensions, and even time itself could operate in different ways. If the multiverse exists, it would mean that our cosmos, vast as it is only a small part of a larger reality. One theory that supports the multiverse is the many worlds interpretation of quantum mechanics. According to this interpretation, every possible outcome of a quantum event actually occurs, creating a new, parallel universe for each possibility. In this view, there could be an infinite number of universes, each with a slightly different history. In one universe, you may have taken a different career path, or stars may have formed in different places. These alternate realities would exist side by side, yet be completely inaccessible to us. Another approach to the multiverse comes from the theory of cosmic inflation. This theory posits that, in the moments following the Big Bang, the universe underwent a rapid expansion, creating bubble universes that branched off and continued to evolve independently. In some of these bubble universes, the fundamental constants of nature, such as the speed of light, the force of gravity, or the charge of an electron could differ, leading to universes vastly different from our own. Some might be filled with black holes, while others could be completely devoid of stars or even matter. The multiverse is also explored in string theory, which suggests that there may be multiple dimensions beyond the familiar three dimensions of space and one of time. In some versions of string theory, our universe is just a brane, a three-dimensional surface floating in a higher dimensional space. According to this idea, other branes could exist parallel to ours, each representing a separate universe with its own unique properties. In these higher dimensions, our universe could be only one of many, with branes colliding or interacting in ways that produce new universes or even create observable effects, such as gravitational waves. The concept of a multiverse challenges our understanding of existence, raising profound questions about the nature of reality and our place in it. If the multiverse exists, it would imply that everything we know and experience is only one facet of a much grander structure, a vast and incomprehensible web of worlds and possibilities. It also raises ethical and philosophical questions. If there are infinite versions of ourselves in different universes, what does that mean for free will, identity, and individuality? Are we unique, or just one of countless variations? While the multiverse remains a theoretical concept, scientists are exploring ways to test its implications. For example, if two bubble universes were to collide, they might leave an imprint on the cosmic microwave background radiation. Researchers are also studying the possibility of detecting gravitational waves or other signatures that could indicate the presence of higher dimensions. Although these ideas are speculative, they represent the frontier of scientific thought, challenging us to expand our understanding of reality and consider the possibility that our universe is part of an unimaginably vast and intricate cosmic landscape. Dark energy, the force accelerating the universe's expansion. Dark energy is one of the most profound and mysterious forces in the universe, driving the accelerated expansion of space and accounting for approximately 68% of the universe's total energy density. Its discovery in the late 1990s fundamentally altered our understanding of cosmology, revealing that the universe is not only expanding but doing so at an ever-increasing rate. Despite its immense influence, the true nature of dark energy remains one of the greatest unsolved mysteries in science. The story of dark energy begins with the observation of distant Type Ia supernovae explosions of white dwarf stars that serve as standard candles for measuring cosmic distances. In the 1990s, two independent research teams used these supernovae to map the universe's expansion history. To their astonishment, they found that the expansion of the universe was not slowing down, as previously assumed, but accelerating. This unexpected discovery suggested the presence of a repulsive force, later termed dark energy, counteracting the pull of gravity on cosmic scales. Dark energy's effects are most evident in the behavior of galaxies over vast distances. As space expands, galaxies are carried apart like raisins in a rising loaf of bread. However, the acceleration caused by dark energy means that galaxies farther away are receding from us faster than those nearby. This phenomenon, first observed by Edwin Hubble in the early 20th century, now carries a deeper significance, as it highlights the dynamic and ever-changing nature of the cosmos. The leading explanation for dark energy is the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Einstein initially included the cosmological constant to allow for a static universe, unaware at the time that the universe was expanding. After Hubble's discovery of cosmic expansion, Einstein famously referred to the constant as his greatest blunder. However, with the discovery of dark energy, the cosmological constant has gained new relevance, representing a form of energy inherent to the fabric of space itself. In this interpretation, dark energy is a constant energy density that fills space uniformly. As the universe expands, new space is created, and with it, more dark energy causing the expansion to accelerate. This model, known as the lambda-cold dark matter (LAC model), is the current standard in cosmology, successfully explaining many observed phenomena, including the large-scale structure of the universe and the anisotropies in the cosmic microwave background (CMB). Alternative theories propose that dark energy might not be constant but dynamic, evolving over time. These models, often referred to as quintessence, suggest that dark energy is a field that changes in strength as the universe expands. Unlike the cosmological constant, quintessence allows for variations in the rate of cosmic acceleration, potentially offering explanations for subtle discrepancies in observational data. However, such models require additional parameters and have yet to gain the same level of empirical support as the cosmological constant. Dark energy's influence extends far beyond the present. It plays a crucial role in determining the ultimate fate of the universe. If dark energy remains constant, the universe will continue to expand indefinitely, leading to a big freeze. In this scenario, galaxies will drift farther apart, stars will exhaust their nuclear fuel, and the cosmos will grow increasingly cold and dark over trillions of years. Alternatively, if dark energy's strength increases, it could lead to a big rip, where the expansion becomes so rapid that galaxies, stars, planets, and even atoms are torn apart. Conversely, if dark energy diminishes or reverses, the universe could collapse in a big crunch, returning to a hot, dense state similar to the conditions of the Big Bang. This cyclical model, while less favored by current observations, offers intriguing possibilities for a universe that perpetually renews itself. Observing dark energy directly is challenging, as it does not emit, absorb, or reflect light. Instead, its presence is inferred through its effects on the universe's expansion and the distribution of galaxies. Large-scale surveys, such as the Dark Energy Survey (DS) and the Euclid mission, aim to map the three-dimensional structure of the universe with unprecedented precision, providing new insights into dark energy's properties. These surveys measure phenomena such as baryon acoustic oscillations, ripples in the density of matter from the early universe, and weak gravitational lensing, the bending of light by mass, to refine our understanding of cosmic acceleration. One of the most intriguing aspects of dark energy is its connection to fundamental physics. Some theories suggest that dark energy could be linked to quantum fluctuations of the vacuum, where particles and antiparticles spontaneously appear and annihilate. Others propose that it might signal the breakdown of general relativity on large scales, pointing to the need for a more comprehensive theory of gravity. These possibilities highlight the profound implications of dark energy for our understanding of the universe's fundamental forces and components. The study of dark energy exemplifies the intersection of observation, theory, and imagination in science. It challenges us to confront the limits of our knowledge and to seek explanations for phenomena that lie beyond the reach of current models. By exploring the nature of dark energy, we not only deepen our understanding of the cosmos, but also illuminate the profound mysteries that define existence itself. Dark energy is a reminder that the universe is not static but dynamic and evolving. It forces us to question long-held assumptions about the nature of space, time, and matter, pushing the boundaries of human knowledge. As we continue to probe its secrets, dark energy promises to transform our understanding of the universe, offering a glimpse into the forces that shape its past, present, and future. The cosmic web, the universe's hidden skeleton. The cosmic web is the vast, interconnected structure of the universe, a network of filaments composed of dark matter, gas, and galaxies that stretches across hundreds of millions of light years. This intricate framework underpins the distribution of matter in the cosmos, connecting galaxy clusters and leaving vast empty regions known as voids. The cosmic web is not just a visual marvel, it is a fundamental component of the universe, revealing the influence of gravity and dark matter on cosmic evolution. The origins of the cosmic web trace back to the earliest moments after the Big Bang. During the universe's infancy, small quantum fluctuations in density were amplified by gravity, creating regions of higher and lower density. These fluctuations were imprinted in the cosmic microwave background, CMB, and served as the seeds for the formation of large-scale cosmic structures. Over billions of years, gravity pulled matter into dense regions, forming the filaments and nodes that define the cosmic web. The filaments of the cosmic web act as highways for matter, channeling gas and dark matter into galaxy clusters at the intersections of filaments. These dense regions, or nodes, are the sites of intense star formation and galaxy evolution. Between the filaments lie cosmic voids, vast, empty expanses where galaxies are few and far between. These voids can span tens to hundreds of millions of light years, creating a stark contrast to the densely packed filaments and clusters. Mapping the cosmic web has been a monumental achievement in modern astronomy. Large-scale surveys like the Sloan Digital Sky Survey, SES, have cataloged millions of galaxies, revealing the three-dimensional structure of the universe. These maps show how galaxies cluster along filaments, creating a spiderweb-like pattern that stretches across space. The distribution of galaxies in these surveys matches the predictions of cosmological simulations, confirming the role of dark matter in shaping the cosmic web. Dark matter is the invisible backbone of the cosmic web. While it does not emit or absorb light, its gravitational pull shapes the distribution of ordinary matter, guiding the formation of galaxies and clusters. Simulations of the universe's evolution, such as the Millennium Simulation and Illustris project, show how dark matter halos form around dense regions, attracting gas and forming the foundations for galaxies. Without dark matter, the cosmic web as we know it would not exist. The cosmic web is also a dynamic structure, evolving over billions of years. As the universe expands, filaments stretch and grow, while voids become emptier. Interactions between galaxies and clusters within the web drive cosmic evolution, triggering starbursts, supernovae, and the growth of supermassive black holes. These processes enrich the surrounding gas with heavy elements, spreading the building blocks of stars, planets, and life throughout the universe. Studying the cosmic web provides insights into the role of dark energy in shaping the universe. The accelerated expansion of space, driven by dark energy, affects the growth of cosmic structures, slowing the rate at which filaments and clusters form. By measuring the distribution and motion of galaxies within the web, astronomers can refine our understanding of dark energy's properties and its influence on the cosmos. One of the most exciting aspects of the cosmic web is its potential to reveal the origins of the universe. The patterns of density fluctuations in the web carry information about the conditions of the early universe, including the effects of inflation, a rapid expansion that occurred in the first fraction of a second after the Big Bang. By analyzing the distribution of matter in the cosmic web, scientists can test theories of inflation and probe the fundamental physics that govern the universe's birth. The cosmic web also serves as a laboratory for studying the interplay between galaxies, gas, and dark matter. Observations of gas flowing along filaments into clusters, known as the circumgalactic medium, provide clues about the processes that fuel star formation and black hole growth. These flows of matter are critical for understanding how galaxies evolve over time and how they maintain the balance between creation and destruction. Void regions within the cosmic web are equally fascinating. These vast, empty spaces provide a unique environment for studying the universe's expansion and testing theories of gravity. Because voids are dominated by dark energy rather than matter, they offer a clean laboratory for observing the effects of cosmic acceleration. Researchers have even proposed using voids to test alternative theories of gravity, such as modifications to general relativity. The study of the cosmic web is an ongoing effort, combining observations, simulations, and theoretical models to uncover the underlying structure of the universe. Future surveys, such as those conducted by the Vera C. Rubin Observatory and the Euclid mission, will provide even more detailed maps of the web, capturing its evolution over time and refining our understanding of dark matter and dark energy. The cosmic web is a testament to the interconnectedness of the universe. It shows how the smallest fluctuations in the early cosmos grew into the vast structures we see today, linking galaxies, clusters, and filaments in a grand cosmic tapestry. By exploring the web, we gain a deeper appreciation for the forces that shape the universe and our place within its intricate design. The evolution of stars, from formation to their spectacular endings. Stars are the engines of the universe, forging elements, radiating energy, and shaping the environments around them. Their life cycles span millions to billions of years, defined by a delicate balance between gravity and the energy released through nuclear fusion. Understanding the evolution of stars not only reveals the processes that govern their lifetimes, but also provides insight into the origins of the elements that make up everything we see, including life itself. Stars begin their lives in vast molecular clouds, regions of cold gas and dust scattered throughout galaxies. These clouds, often stretching across light years, are the nurseries of stellar birth. Within them, regions of higher density collapse under their own gravity, forming protostars. During this phase, gravitational energy is converted into heat, and the protostar begins to shine faintly. Eventually, when the core temperature reaches approximately 10 million Kelvin, hydrogen fusion ignites, marking the birth of a true star. The main sequence phase of a star's life is its most stable and longest-lasting period. During this time, the star fuses hydrogen into helium in its core, generating energy that counteracts the inward pull of gravity. The star's mass determines its position on the Hertzsprung-Russell (HR) diagram and its overall lifespan. Low-mass stars, like red dwarfs, burn their hydrogen slowly, living for tens to hundreds of billions of years, far longer than the current age of the universe. Medium-mass stars, such as the Sun, spend around 10 billion years on the main sequence before transitioning to later stages. High-mass stars, on the other hand, burn through their fuel rapidly, living for only a few million years. As a star exhausts its hydrogen fuel, its fate diverges based on its mass. Low and medium mass stars expand into red giants as their cores contract and their outer layers swell. In these stars, helium fusion begins, creating heavier elements like carbon and oxygen. Once the star runs out of helium, its outer layers are ejected, forming a planetary nebula, while the core becomes a white dwarf. These remnants, composed mostly of carbon and oxygen, gradually cool and fade over billions of years. High-mass stars undergo a far more dramatic transformation. After leaving the main sequence, they enter a series of fusion stages, creating progressively heavier elements in their cores. This process continues until iron is formed, the most stable element in terms of nuclear binding energy. Iron cannot undergo fusion to produce energy, so the core collapses under gravity, triggering a supernova explosion. These explosions release enormous amounts of energy, briefly outshining entire galaxies and scattering heavy elements into space. Supernovae are not just endings but also beginnings. The elements created in the cores of massive stars and during the explosion itself, such as gold, silver, and uranium, are expelled into the interstellar medium, enriching future generations of stars and planets. Without supernovae, the universe would lack the diversity of elements needed for complex chemistry and life. These explosions also trigger the formation of new stars by compressing nearby gas clouds, continuing the cycle of a letter evolution. The remnants of supernovae depend on the star's mass. Stars with core masses between about 1.4 and 3 times the Sun's mass form neutron stars, ultra-dense, composed almost entirely of trons. These remnants are often found spinning rapidly and emitting beams of radiation, becoming pulsars. For the most massive stars, the core collapses into a black hole, a region where gravity is so intense that nothing, not even light, can escape. The evolution of binary stars introduces additional complexity. In these systems, mass transfer between stars can lead to phenomena such as type Iowa supernovae, which occur when a white dwarf accretes enough material from its companion to trigger a runaway fusion reaction. These explosions serve as standard candles for measuring cosmic distances, playing a critical role in our understanding of the universe's expansion. Stars also shape their environments through stellar wind streams of charged particles that carry away mass and energy. Massive stars, in particular, produce powerful winds that sculpt the surrounding gas, creating stunning nebulae and influencing the formation of nearby stars. These winds, combined with radiation pressure, help regulate star formation rates within galaxies. The study of stars extends beyond their life cycles to their broader impact on the cosmos. Stars are the primary sources of light and heat in the universe, driving the chemistry of planets and providing the conditions necessary for life. Their death seed galaxies with the elements needed for new stars and planetary systems, ensuring the continuity of cosmic evolution. Through observations with telescopes like Hubble and James Webb, as well as simulations of stellar dynamics, scientists continue to uncover the intricacies of stellar evolution. Each phase of a star's life offers a glimpse into the physical processes that govern the universe, from the fusion reactions in stellar cores to the explosive forces of supernovae. By studying stars, we not only learn about their lifetimes but also gain insight into the interconnected cycles that shape galaxies, influence cosmic structures, and create the conditions for life. Stars remind us that the universe is a place of both creation and destruction, where the death of one star can give rise to the birth of another. Their life cycles are a testament to the dynamic and ever-changing nature of the cosmos, a process that has been unfolding for billions of years and will continue for billions more. Through the light of the stars, we see the story of the universe itself, written across time and space. The James Webb Space Telescope, a new era of cosmic exploration. The James Webb Space Telescope, JWST, often called the successor to the Hubble Space Telescope, represents a transformative leap in humanity's ability to observe and understand the universe. Launched in December 2021, after decades of meticulous planning and engineering, JWST is the most powerful and complex space observatory ever built. Its mission is to peer into the deepest corners of the cosmos, unveiling the secrets of the universe's earliest moments, the birth and evolution of galaxies, and the atmospheric compositions of distant exoplanets. One of JWST's most groundbreaking features is its ability to observe in the infrared spectrum, a capability that sets it apart from its predecessor, Hubble, which primarily observes invisible and ultraviolet light. Infrared light has longer wavelengths than visible light, allowing it to pass through dust clouds that obscure many cosmic phenomena. This ability enables JWST to study regions like stellar nurseries, dense molecular clouds where stars and planets form with unparalleled clarity. The telescope's infrared vision also makes it uniquely suited to study the early universe. Due to the expansion of space, light from the first galaxies formed after the Big Bang has been stretched, or redshifted, into the infrared part of the spectrum. JWST can detect this ancient light, providing a window into a time when the universe was just a few 100 million years old. By studying these early galaxies, JWST aims to answer fundamental questions about how the first structures formed, how they evolved, and how they contributed to the reionization of the universe, a pivotal era when light began to travel freely through space. JWST's ability to observe faint, distant objects is due to its massive primary mirror, which measures 6.5 meters in diameter, more than twice the size of Hubble's mirror. composed of 18 hexagonal segments coated in a thin layer of gold for optimal infrared reflectivity. The mirror collects and focuses light with extraordinary precision. To keep the telescope cool and ensure the purity of its infrared observations, JWST is equipped with a multi-layered sun shield the size of a tennis court. This shield blocks heat from the Sun, Earth, and Moon, maintaining the telescope at an operating temperature of about -233 degrees Celsius, -388 degrees Fahrenheit. One of JWST's most exciting areas of research is the study of exoplanets and their atmospheres. By observing the light from a host star as it filters through an exoplanet's atmosphere during a transit, JWST can analyze the atmospheric composition of these distant worlds. This technique, known as transmission spectroscopy, allows scientists to identify key molecules such as water vapor, carbon dioxide, methane, and oxygen, potential indicators of habitability or even life. The telescope's early observations have already yielded groundbreaking results. JWST detected carbon dioxide in the atmosphere of an exoplanet for the first time and has begun characterizing the atmosphere of rocky planets' inhabitable zones. These studies are paving the way for the search for biosignatures, chemical markers that suggest the presence of life. While JWST cannot directly image Earth like planets in the habitable zones of Sun-like stars, its findings will design of future missions aimed at detecting signs of life on other worlds. In addition to its studies of the early universe and exoplanets, JWST is providing new insights into the life cycles of stars. It has captured stunning images of stellar nurseries, such as the Carina Nebula, where young stars are carving out intricate shapes in surrounding clouds of gas and dust. JWST is also probing the final stages of stellar evolution, observing the complex structures of planetary nebulae and the environments around remnants supernova remnants. The telescope's capabilities extend to the study of galaxies across cosmic time. By observing galaxies at different stages of their evolution, JWST is unraveling the processes that drive their growth and transformation. It is shedding light on how supermassive black holes influence their host galaxies, how galaxies merge and interact, and how star formation rates have changed over billions of years. These observations are providing a more complete picture of the universe's history and the mechanisms that shape its large-scale structure. JWST is also contributing to our understanding of our own solar system. Its infrared observations are revealing new details about the atmospheres of gas giants like Jupiter and Saturn, the icy surfaces of moons such as Europa and Enceladus, and the composition of comets and asteroids. These studies are helping scientists piece together the history of the solar system and assess its potential for supporting life beyond Earth. The telescope's journey to success has not been without challenges. Delayed numerous times due to technical and budgetary issues, JWST's eventual launch and deployment required an unprecedented level of precision and coordination. Its intricate unfolding process, likened to an origami masterpiece, was a high-stakes operation involving the deployment of its sun shield, mirror segments, and instruments over the course of several weeks. The flawless execution of this process was a testament to the ingenuity and perseverance of the international team of scientists, engineers, and technicians behind the mission. JWST is a collaborative effort involving NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. This partnership has brought together expertise and resources from around the world, reflecting the shared goal of advancing humanity's understanding of the cosmos. The telescope's discoveries are freely shared with the global scientific community, fostering collaboration and inspiring a new generation of researchers. The James Webb Space Telescope is more than an instrument. It is a symbol of human curiosity and our relentless drive to explore the unknown. Its observations are rewriting textbooks, expanding our understanding of the universe, and inspiring us to ask new questions about our place in the cosmos. As it continues to operate over the coming decades, JWST will undoubtedly phenomena we cannot yet imagine, reminding us of the boundless possibilities of science and exploration. The birth of the solar system, from dust to planets. The formation of our solar system is a story that stretches back over 4.5 billion years, rooted in the dynamic process of a vast molecular cloud in our galaxy. This cosmic event gave rise to the sun, the planets, moons, asteroids, and comets that form the intricate system we inhabit today. Understanding how the solar system came to be offers not only a glimpse into our own origins, but also insights into the processes shaping planetary systems across the cosmos. The story begins in a molecular cloud, a cold, dense region of gas and dust where stars are born. Within this cloud, a disturbance, possibly triggered by a nearby supernova explosion or the gravitational pull of a passing star, caused a region to collapse under its own gravity. As the cloud fragmented, one such region formed a dense core, which would become the solar nebula. This disk-shaped structure of gas and dust rotated rapidly as it contracted, with most of the material pulled toward the center, forming the protoson. The proton grew hotter and denser as gravitational energy was converted into heat, igniting nuclear fusion when the temperature reached around 10 million Kelvin. This marked the birth of the sun, the center of the nascent solar system. Surrounding the sun, the remaining gas and dust in the solar nebula provided the raw material for planet formation. The process of planetary formation began with the aggregation of tiny particles in the disk. These particles collided and stuck together through electrostatic forces, forming larger clumps called planetesimals. Over time, these planetesimals grew into protoplanets through continued collisions and gravitational attraction. The inner regions of the disk, where temperatures were higher, gave rise to rocky planets like Earth and Mars, as volatile compounds like water and methane were driven away by the sun's heat. In contrast, the cooler outer regions allowed gas giants like Jupiter and Saturn to form, accumulating thick atmospheres of hydrogen and helium. The formation of the gas giants played a critical role in shaping the solar system. Their immense gravitational influence sculpted the orbits of smaller bodies and cleared the surrounding space of debris. Jupiter, in particular, acted as a cosmic shield, deflecting many comets and asteroids that might otherwise have collided with the inner planets. However, it also destabilized some orbits, sending objects into the inner solar system, where they contributed to the heavy bombardment period, a time of intense asteroid and comet impacts that left lasting scars on planetary surfaces. The final stages of solar system formation were marked by a period of dynamic interactions and migrations. The young planets jockeyed for position, their orbits influenced by gravitational interactions with each other, and the remnants of the solar nebula. This era, known as the Nice model after the city in France where it was developed, explains many features of the current solar system, such as the distribution of asteroids and the peculiar orbits of distant objects like Pluto. The Moon, Earth's closest companion, also owes its existence to the chaotic early solar system. The leading theory suggests that a Mars-sized body, named Theia, collided with the proto-Earth around 4.5 billion years ago. The impact ejected vast amounts of material into orbit, which coalesced to form the Moon. This event not only gave Earth a natural satellite, but also helped stabilize its axial tilt, contributing to the development of stable seasons and a hospitable climate. As the solar system matured, leftover debris formed the asteroid belt, Kuiper belt, and Oort cloud. The asteroid belt, located between Mars and Jupiter, consists of rocky remnants that never coalesced into a planet, likely due to Jupiter's gravitational interference. The Kuiper belt, beyond Neptune, is home to icy bodies like Pluto and Haumea, while the Oort cloud, a theoretical shell of icy objects, represents the distant frontier of the solar system, stretching nearly a light year from the sun. Water, a critical ingredient for life on Earth, likely arrived during the late heavy bombardment period, delivered by icy comets and asteroids. These impacts enriched the young Earth with the volatile compounds necessary for its oceans and atmosphere, setting the stage for the emergence of life. Recent studies also suggest that Earth's interior may have contained significant water from its formation, indicating a complex interplay of sources. The study of solar system formation continues to evolve, driven by observations of exoplanetary systems and advances in simulation technology. Comparing our solar system to others has revealed both striking similarities and intriguing differences. Many exoplanet systems host super-Earths and hot Jupiters, types of planets that are absent in our solar system. These findings challenge existing models and suggest that our system may be an outlier in some respects. Missions like NASA's OSIRIS-REx, which recently returned samples from the asteroid Bennu, and ESA's Rosetta, which studied the comet 67P Churyumov-Gerasimenko, are providing direct insights to the building blocks of the solar system. These pristine materials offer a window into the conditions and processes that prevailed during the system's formation, helping scientists refine their models and answer long-standing questions.
The formation of the solar system is a tale of chaos and creativity, a process of destruction and renewal that transformed a cloud of gas and dust into a complex and dynamic system. Each planet, moon, and asteroid carries the imprint of this history, offering clues about the forces that shaped it. By studying these objects, we not only learn about our own origins, but also gain a deeper understanding of the universal processes that govern planetary systems across the cosmos.
The birth and death of the universe, cycles of creation and destruction. The universe, vast and seemingly eternal, has a finite history that began approximately 13.8 billion years ago with the Big Bang. Its story is one of constant evolution, marked by cycles of creation and destruction that continue to shape its structure and dynamics. While much has been uncovered about its origins and growth, the ultimate fate of the cosmos remains one of the most profound mysteries in science. The beginning, the Big Bang and cosmic inflation. The universe began as an incomprehensibly hot and dense point of singularity. In the first fractions of a second after the Big Bang, the universe underwent an era of rapid expansion known as cosmic inflation. During this phase, the universe expanded exponentially, smoothing out irregularities and laying the groundwork for the large-scale structure observed today. Inflation stretched quantum fluctuations to macroscopic scales, seeding the tiny variations in density that would later grow into galaxies, clusters, and the cosmic web. As inflation ended, the universe transitioned into the hot Big Bang phase, filled with a dense plasma of particles. During the first few minutes, a process called primordial nucleosynthesis produced the light elements hydrogen, helium, and trace amounts of lithium. For the next 380,000 years, the universe was opaque, as photons continuously interacted with free electrons in the plasma. This era ended with recombination, when electrons bonded with nuclei to form neutral atoms, allowing light to travel freely. The resulting radiation, now observed as the cosmic microwave background, CMB, provides a snapshot of the universe at this pivotal moment. The growth, structure formation, and the role of dark matter. After recombination, the universe entered the Dark Ages, a period before the formation of the first stars. During this time, gravity amplified the density fluctuations seeded during inflation, drawing matter into the first clumps. These clumps, composed primarily of dark matter, served as scaffolds for the formation of galaxies. Hydrogen and helium gas accumulated in these regions, eventually collapsing to form the first stars and galaxies. The first stars, known as population III stars, were massive and short-lived, ending their lives in powerful supernovae that enriched the surrounding gas with heavier elements. This enrichment enabled the formation of more complex structures, including the first planetary systems. Over billions of years, galaxies grew through mergers and accretion, forming the vast cosmic web of filaments and clusters observed today. Dark matter played a critical role in this process. Its gravitational influence dictated the distribution of ordinary matter, shaping the large-scale structure of the universe. Without dark matter, the universe would lack the intricate web of galaxies and clusters that define its structure. The accelerating universe, the role of dark energy. In the 20th century, astronomers discovered that the universe is expanding, a finding attributed to the work of Edwin Hubble. Initially, it was believed that this expansion was slowing due to the pull of gravity. However, observations of distant Type Iowa supernovae in the late 1990s revealed that the expansion is accelerating, driven by a mysterious force known as dark energy. This discovery fundamentally changed our understanding of the universe, indicating that dark energy dominates its energy budget, accounting for about 68% of its total content. Dark energy's influence grows as the universe expands, pulling galaxies apart and preventing the formation of new structures. Over time, it is expected to lead to a state of isolation, where galaxies drift so far apart that they become invisible to each other. This scenario, often referred to as the Big Freeze, suggests a cold and dark future for the universe. The end. Theories of cosmic fate. The ultimate fate of the universe depends on the interplay between dark energy, dark matter, and gravity. Several scenarios have been proposed.
The Big Freeze. If dark energy remains constant, the universe will continue expanding indefinitely. Over trillions of years, star formation will cease as galaxies exhaust their gas reserves. Existing stars will burn out, leaving only black holes, white dwarfs, and neutron stars. Even these remnants will eventually decay through processes like Hawking radiation, leaving a cold and empty cosmos.
The Big Rip. In some models, dark energy's strength increases over time. If this occurs, it could tear apart galaxies, stars, planets, and even a catastrophic event known as the Big Rip. This scenario represents the ultimate triumph of dark energy over all other forces. The Big Crunch and Big Bounce. If dark energy reverses or weakens, the universe could stop expanding and begin contracting. This contraction could culminate in a Big Crunch, where the universe collapses back into a hot, dense state. Some theories suggest that this collapse might trigger a new Big Bang, initiating a cyclical model of expansion and contraction, a Big Bounce. Vacuum decay. The universe may exist in a metastable state with a false vacuum energy level. A quantum fluctuation could cause it to transition to a lower energy true vacuum, resulting in a bubble of destruction that propagates at the speed of light, altering the universe's fundamental laws. Probing the universe's fate. Astronomers and physicists are actively investigating these scenarios by studying the properties of dark energy, the distribution of dark matter, and the universe's large-scale structure. Observatories like the Dark Energy Survey, DEES the Euclid mission, and the Vera C. Rubin Observatory are mapping the cosmos in unprecedented detail, measuring the effects of dark energy on galaxy clustering and the expansion rate. Gravitational wave observatories, such as LIGO and Virgo, are also contributing by detecting signals from merging black holes and neutron stars, which offer insights into the universe's evolution. Meanwhile, particle physics experiments aim to uncover the nature of dark matter and its interactions with ordinary matter, which could have profound implications for understanding the universe's ultimate fate. The cycle of creation and destruction. While the end of the universe remains uncertain, its story is one of continuous cycles. Stars form from the remnants of previous generations, galaxies grow through mergers, and elements forged in stellar cores are recycled into new stars and planets. Even in the distant future, when the cosmos may seem barren, the processes that defined its early history, gravity, thermodynamics, and quantum mechanics, will continue to shape its evolution. The birth and death of the universe remind us of the dynamic nature of the cosmos. It is a place of constant change, where destruction often paves the way for creation. By studying the universe's history and contemplating its future, we gain not only scientific insights, but also a deeper appreciation for the intricate interconnected forces that define existence itself. The role of black holes in galactic evolution. Black holes, once considered enigmatic anomalies of the universe, are now recognized as critical players in the evolution of galaxies. These cosmic giants, ranging from stellar mass black holes to supermassive behemoths millions or billions of times the sun's mass, influence their surroundings in profound ways. Their gravitational pull, energy output, and interactions with nearby matter shape the structure and behavior of galaxies, making them central to the cosmic story.
Supermassive black holes, the anchors of galaxies.
At the heart of nearly every large galaxy lies a supermassive black hole. The Milky Way, for instance, harbors Sagittarius A, a black hole with a mass of about 4 million suns. These central black holes act as gravitational anchors, influencing the motions of stars and gas within their host galaxies. Observations of stars orbiting Sagittarius A, for example, have provided direct evidence of its presence, with their rapid, elliptical motions pointing to an incredibly dense, invisible object. While the exact origins of supermassive black holes remain a mystery, they are thought to have formed from the collapse of massive gas clouds in the early universe, or from the growth of smaller black holes through mergers and accretion. Regardless of their beginnings, these black holes have grown over billions of years, consuming surrounding matter and merging with other black holes during galaxy collisions. Active galactic nuclei and quasars. When a supermassive black hole actively accretes matter, it can transform into an active galactic nucleus, AGN, emitting vast amounts of energy. As gas and dust spiral into the black hole, they form an accretion disk that becomes heated to millions of degrees, radiating in X-rays, ultraviolet, and visible light. AGNs can outshine their host galaxies, making them some of the brightest objects in the universe. Quasars, the most luminous type of AGN, are powered by supermassive black holes consuming matter at astonishing rates. Observed in the distant universe, quasars provide a glimpse into the early stages of galaxy evolution, when black holes and their host galaxies were still forming. The energy output of quasars can have dramatic effects on their surroundings, driving away gas and halting star formation in a process known as quenching. This feedback mechanism plays a key role in regulating the growth of galaxies. Feedback mechanisms shaping galaxies. Black holes exert influence far beyond their immediate surroundings through feedback processes. As matter falls into a black hole, it releases energy that can heat or expel gas in the host galaxy. This feedback comes in two primary forms, radiative and kinetic. Radiative feedback involves the intense radiation from the accretion disk, which heats the surrounding gas and prevents it from cooling and condensing into stars. Kinetic feedback, on the other hand, is driven by powerful jets of particles launched from the poles of the accretion disk at near light speeds. These jets can extend thousands of light years, carving out cavities in galaxy clusters and redistributing matter across vast distances. These feedback processes are crucial for understanding the co-evolution of galaxies and their central black holes. Observations show a correlation between the mass of a galaxy's central black hole and the properties of its bulge, such as its mass and velocity dispersion. This relationship, known as the M-sigma relation, suggests a close connection between black hole growth and galaxy evolution, likely mediated by feedback. Black holes and galaxy mergers. Galaxy mergers are among the most dramatic events in the universe, and black holes play a central role in these cosmic collisions. When two galaxies merge, their central black holes are drawn together, forming a binary system. Over time, these black holes spiral inward, emitting gravitational waves as they lose energy. The final stages of this process, when the black holes merge, produce powerful gravitational wave signals that can be detected by observatories like LIGO and Virgo. The merger of galaxies and their black holes triggers bursts of star formation, as gas clouds collide and compress. However, the energy released by the merging black holes can also expel gas, quenching star formation and leaving behind a more passive galaxy. These interactions help explain the transition of galaxies from blue, star-forming systems to red, quiescent ones. Primordial black holes in early galaxy formation. In addition to supermassive black holes, the early universe may have hosted primordial black holes, hypothetical remnants from the Big Bang. These objects, if they exist, could have served as seeds for the formation of supermassive black holes, providing a head start in their growth. They may also contribute to the mysterious dark matter that makes up about 27% of the universe's total mass energy content. Primordial black holes, if detected, could offer insights into the universe's first moments, shedding light on the conditions that prevailed during cosmic inflation. Efforts to detect these elusive objects involve studying gravitational lensing, gamma-ray bursts, and the cosmic microwave background for subtle signals of their presence. Observing black holes, challenges and advances. Despite their influence, black holes are notoriously difficult to observe directly. Their defining feature, the event horizon, allows no light or matter to escape, rendering them invisible. However, indirect methods have provided a wealth of information. Observing the orbits of stars near the galactic center, for instance, has revealed the mass and location of supermassive black holes. In 2019, the Event Horizon Telescope, EAT, captured the first ever image of a black hole's shadow, located in the galaxy M87. This image confirmed theoretical predictions and provided a direct glimpse of the warped space-time near the event horizon. Future observations with the EAT and other instruments aim to study black hole accretion disks, magnetic fields, and jet formation in greater detail. Black holes, cosmic architects. Black holes are not merely endpoints of stellar evolution, they are active participants in the cosmic dance, shaping the growth and behavior of galaxies. Their gravitational pull influences the motion of stars, while their feedback processes regulate star formation and gas distribution. Through their interactions with surrounding matter, black holes drive the evolution of galaxies, contributing to the dynamic and ever-changing universe. The study of black holes offers a window into the universe's most extreme conditions, where gravity, space, and time are stretched to their limits. By unraveling their mysteries, we not only learn about the forces that govern galaxies, but also gain deeper insights into the nature of space-time, the evolution of the cosmos, and our place within it. Time and space, the fabric of the universe. Time and space are the foundational dimensions of our universe, intricately woven into the fabric of existence. Albert Einstein's theories of relativity transformed our understanding of these concepts, showing that they are not fixed and independent but interconnected and malleable. Together they form space-time, a dynamic framework influenced by matter, energy, and motion. This revolutionary perspective has reshaped our understanding of the cosmos and the forces that govern it. The nature of space-time. In classical physics, space and time were seen as separate and absolute. Time ticked away uniformly, and space provided a static backdrop for matter in motion. Einstein's special theory of relativity, published in 1905, shattered this notion by demonstrating that time and space are relative, changing depending on the observer's velocity. At the heart of this theory is the concept that the speed of light is constant for all observers, regardless of their motion. This constancy leads to phenomena such as time dilation and length contraction. Time dilation occurs when an object moves close to the speed of light. To an outside observer, time for that object appears to slow down. This effect has been confirmed through experiments with high-speed particles and atomic clocks on fast-moving spacecraft. Length contraction, on the other hand, describes how an object in motion appears shorter along its direction of travel to a stationary observer. Together, these effects show that time and space are not absolute but are interwoven into a single continuum, space-time. Einstein's general theory of relativity, introduced in 1915, expanded on this concept by incorporating gravity into the framework of space-time. In this theory, gravity is not a force acting at a distance, as Isaac Newton proposed, but a curvature in space-time caused by mass and energy. Massive objects, like stars and planets, warp the fabric of space-time, creating the effects we perceive as gravity. This curvature influences the motion of other objects, guiding planets in their orbits and bending the paths of light. Gravity and the warping of space-time. One of the most striking predictions of general relativity is the bending of light by gravity, a phenomenon known as gravitational lensing. When light from a distant object, such as a galaxy, passes near a massive foreground object, the curvature of space-time bends the light, magnifying and distorting the image. Gravitational lensing has become a powerful tool for studying the universe, allowing astronomers to map the distribution of dark matter and observe distant galaxies that would otherwise be too faint to detect. The warping of space-time is also responsible for the slowing of time near massive objects, an effect known as gravitational time dilation. For example, time moves more slowly on the surface of the Earth compared to a satellite in orbit. This effect, though imperceptible in everyday life, is critical for technologies like GPS, which rely on precise timing to provide accurate location data. Without accounting for general relativity, GPS systems would accumulate errors of several kilometers each day. In extreme cases, such as near a black hole, the warping of space-time becomes so intense that time appears to stop entirely for an outside observer. This region, known as the event horizon, marks the boundary beyond which nothing, not even light, can escape. The study of black holes offers a unique window into the interplay of gravity and space-time, testing the limits of general relativity under the most extreme conditions. Space-time and the expansion of the universe. Space-time is not static but dynamic, stretching and evolving with the universe. The discovery that the universe is expanding, first observed by Edwin Hubble in the 1920s, revealed that space itself is growing, carrying galaxies farther apart. This expansion is not caused by galaxies moving through space, but by the stretching of space-time itself. The further away a galaxy is, the faster it appears to recede, a relationship described by Hubble's law. The acceleration of the universe's expansion, driven by dark energy, adds another layer of complexity to the nature of space-time. Dark energy, thought to be a property of space itself, exerts a repulsive force that counteracts gravity on cosmic scales. As space-time expands, new space is created, amplifying the effects of dark energy and accelerating the expansion. This dynamic interplay shapes the large-scale structure of the universe, influencing the distribution of galaxies and clusters. Time, a flexible dimension. Time, often perceived as a linear progression from past to future, is far more complex in the framework of relativity. The concept of simultaneity, events occurring at the same time, is relative, depending on the observer's motion. This means that two observers moving at different velocities may disagree on the order of events, challenging our intuitive understanding of cause and effect. In certain conditions, time can behave in unexpected ways. Near the speed of light, time dilation becomes extreme, allowing travelers to experience significantly less time than those left behind. This effect, known as the twin paradox, has profound implications for interstellar travel, suggesting that journeys to distant stars could be feasible within a human lifetime for the traveler, though centuries might pass on Earth. Theories about time extend beyond relativity, venturing into quantum mechanics and cosmology. Some speculative ideas suggest that time may emerge from deeper physical principles, rather than being a fundamental aspect of reality. Others propose the existence of multiple timelines or the possibility of time travel, though such concepts remain purely theoretical. The unification of space-time in quantum mechanics. One of the greatest challenges in modern physics is reconciling general relativity, which describes gravity and large-scale phenomena, with quantum mechanics, which governs the behavior of particles on the smallest scales. Space-time, as described by relativity, is smooth and continuous, while quantum mechanics operates in a probabilistic realm, where particles exhibit wave-particle duality and uncertainty. The quest for a unified theory, often referred to as quantum gravity, seeks to describe the behavior of space-time at the Planck scale, an incredibly small distance where quantum effects dominate. Theories like string theory and loop quantum gravity offer potential pathways to this unification, suggesting that space-time itself may have a discrete, granular structure at the smallest scales. The mystery of time and space. Time and space remain deeply mysterious, even as our understanding continues to evolve. They are the stage on which the drama of the universe unfolds, shaping everything from the motion of galaxies to the behavior of particles. By studying space-time, we probe the fundamental nature of reality, uncovering the forces that govern existence and the connections that bind the cosmos together. Through the lens of relativity, we see a universe that is dynamic, interconnected, and far stranger than our everyday experiences suggest. Space and time are not mere dimensions, but the very fabric of the cosmos, woven together in ways that challenge our understanding and inspire our imagination. Nebulae, cradles of stars and the beauty of the cosmos. Nebulae are some of the most breathtaking and vital structures in the universe. These vast clouds of gas and dust serve as the birthplaces of stars and planets, as well as the remnants of stellar death. Their vibrant colors and intricate shapes, captured in stunning detail by telescopes like Hubble and James Webb, reveal the dynamic processes at work in the cosmos. Nebulae are not just visually striking, they are laboratories of creation and transformation, shaping the evolution of galaxies and seeding the universe with the ingredients for life. The types of nebulae. Nebulae come in a variety of forms, each representing a different stage in the life cycle of stars. The most common types include emission nebulae. These are glowing clouds of ionized gas, illuminated by the ultraviolet light from nearby young, hot stars. The energy from these stars excites the gas, causing it to emit light in specific wavelengths. The Orion Nebula, one of the most famous emission nebulae, is a stellar nursery where hundreds of new stars are forming. The vibrant reds and pinks in emission nebulae are often due to hydrogen, the most abundant element in the universe. Reflection nebulae. Unlike emission nebulae, reflection nebulae do not emit their own light. Instead, they scatter and reflect the light of nearby stars. This scattering often gives them a bluish appearance, as shorter wavelengths of light are scattered more effectively. The Pleiades star cluster is surrounded by reflection nebulae, adding a ghostly glow to its bright stars. Dark nebulae. These are dense clouds of gas and dust that block the light from stars and other nebulae behind them. Appearing as dark patches against the backdrop of the Milky Way, dark nebulae are regions of concentrated material where star formation may occur. The Horsehead Nebula is a striking example of this type. Planetary nebulae. Despite their name, planetary nebulae have nothing to do with planets. They are the remnants of dying low to medium mass stars, like our Sun. When such a star exhausts its nuclear fuel, it expels its outer layers, leaving behind a glowing shell of gas and a white dwarf at its center. The Ring Nebula and the Helix Nebula are beautiful examples of this phase of stellar evolution. Supernova remnants. These nebulae are the aftermath of a massive star's explosive death. The material ejected during a supernova expands outward, creating complex and colorful structures. The Crab Nebula is a well-studied supernova remnant, its intricate filaments providing clues about the powerful forces at work during the explosion. The role of nebulae in star formation. Nebulae are the cradles of stars, where the interplay of gravity, pressure, and turbulence drives the formation of new stellar systems. Within a nebula, regions of higher density collapse under their own gravity, forming protostars. As these protostars grow, they heat up and begin nuclear fusion, marking their transformation into true stars. The process of star formation is not uniform. Massive stars form more quickly and can influence their surroundings by emitting powerful winds and radiation. These effects carve out cavities in the nebula, compressing nearby gas and triggering the formation of additional stars. This chain reaction of star formation creates clusters, where stars are born in close proximity, sharing a common origin. The material left over after star formation often coalesces into disks around young stars, where planets, moons, and other celestial bodies can form. The study of protoplanetary disks in nebulae provides insights into the early stages of planetary systems, shedding light on the processes that shaped our own solar system. The death of stars and the creation of nebulae. Nebulae are not only the birthplaces of stars but also the remnants of their deaths. When low to medium mass stars, like our Sun, reach the end of their lives, they shed their outer layers, creating planetary nebulae. The remaining core becomes a white dwarf, a dense and slowly cooling stellar remnant. Massive stars, on the other hand, end their lives in supernovae, scattering heavy elements into space. These explosions create supernova remnants, enriching the interstellar medium with the raw materials for future stars and planets. The elements forged in these explosions, such as carbon, oxygen, and iron, are essential for the formation of complex molecules and life. The colors of nebulae. The vivid colors of nebulae are not just beautiful, but also scientifically revealing. They are produced by the emission or reflection of light at specific wavelengths, corresponding to the elements present in the nebula. Hydrogen, the most abundant element, emits a reddish light when ionized. Oxygen often contributes green or blue hues, while other elements like sulfur and nitrogen add to the palette. These colors allow astronomers to study the composition, temperature, and density of nebulae. By analyzing the light from nebulae, scientists can determine their chemical makeup and understand the processes shaping them. Nebulae as laboratories of chemistry. Nebulae are not only composed of hydrogen and helium, but also contain trace amounts of heavier elements and complex molecules. Within their dense regions, chemical reactions occur, forming molecules like water, carbon dioxide, and ammonia. These molecules are often embedded in icy grains of dust, which can survive the harsh conditions of space. The study of molecular clouds' dense regions within nebulae reveals the presence of organic molecules, including those that are precursors to life. These discoveries suggest that the building blocks of life may be widespread in the universe, transported by comets and meteorites to young planets. The role of nebulae in galactic evolution. Nebulae are essential to the life cycle of galaxies, driving star formation and recycling material. As stars are born, evolve, and die, they interact with their surrounding nebulae, enriching them with heavy elements and shaping their structure. This continuous cycle ensures the renewal of galaxies, maintaining their dynamism and diversity. In starburst galaxies, where star formation occurs at an accelerated rate, nebulae are particularly prominent, glowing brightly in ultraviolet and infrared light. These galaxies provide a glimpse into the processes that dominated the early universe, when star formation was at its peak. The legacy of nebulae. Nebulae are more than beautiful phenomena, they are integral to the universe's life cycle. They are the nurseries of stars, the remnants of stellar death, and the reservoirs of the elements that make up planets and life. By studying nebulae, we uncover the interconnected processes that shape galaxies and learn about the origins of our own existence. Each nebula tells a story, a chapter in the grand narrative of the cosmos. Through their study, we deepen our understanding of the forces that govern the universe, gaining a greater appreciation for the beauty and complexity of the cosmos. Interactions shape the structure and evolution of the cosmos, driving processes like star formation, planetary rearrangements, and even the creation of new galaxies. Though they occur over vast timescales, their effects are profound and far-reaching, leaving indelible marks on the universe. Galactic collisions, the dance of titans. Galaxies, the massive collections of stars, gas, dust, and dark matter, often interact and collide in the vast expanse of space. Despite their seemingly isolated positions, gravitational forces can draw them together, triggering a slow and intricate dance that lasts hundreds of millions of years. The Milky Way itself is on a collision course with the Andromeda Galaxy, an event expected to unfold in about 4.5 billion years. During galactic collisions, individual stars rarely collide due to the immense distances between them. Instead, the interaction primarily involves the gas and dust within the galaxies. As these materials are compressed by tidal forces, they ignite bursts of star formation, known as starbursts. These periods of intense activity can produce thousands of new stars, rapidly transforming the colliding galaxies. The gravitational forces at play also warp the shapes of the galaxies, creating spectacular tidal tails, bridges, and loops. The antennae galaxies, a pair of colliding galaxies, showcase these stunning structures, their elongated arms stretching across space as a testament to the power of gravity. Over time, the merging galaxies may settle into a single, larger galaxy, often elliptical in shape. This process, while destructive, is also creative, as it blends the stars, gas, and dark matter of the original galaxies into a new cosmic entity. Planetary collisions, the origins of moons and systems. On a smaller scale, collisions between planets, moons, and other celestial bodies have played a crucial role in shaping planetary systems. Early in the solar system's history, the young planets frequently collided with leftover planetesimals and each other, sculpting their orbits and compositions. One of the most significant planetary collisions is believed to have formed Earth's moon. According to the giant impact hypothesis, a Mars-sized object named Theia collided with the proto-Earth approximately 4.5 billion years ago. The impact ejected vast amounts of debris into orbit, which coalesced to form the Moon. This event not only gave Earth a natural satellite, but also influenced its axial tilt, stabilizing its climate and fostering conditions for life. Collisions also explain the tilted and irregular orbits of some planets and moons in the solar system. Uranus, for example, rotates on its side, likely the result of a massive impact in its early history. These interactions highlight the chaotic and dynamic nature of planetary formation. Star collisions, rare but spectacular. While rare collisions between stars do occur, particularly in densely packed regions like globular clusters, when two stars collide, they merge to form a single, larger star. These collisions can produce unusual objects, such as blue straggler stars that appear younger and hotter than their neighbors because they have been rejuvenated by the influx of material from a collision. In some cases, stellar collisions trigger violent explosions. When a white dwarf in a binary system accretes enough material from its companion star, it can exceed the Chandrasekhar limit, triggering a type Iowa supernova. These explosions are not only spectacular but also serve as important tools for measuring cosmic distances. Cosmic impacts, the shaping of planetary surfaces. Impacts between asteroids, comets, and planets have left visible scars on planetary surfaces, shaping their landscapes and influencing their evolution. The craters on the Moon, Mars, and Mercury are remnants of ancient impacts during the heavy bombardment period, a time when the solar system was teeming with debris. On Earth, impacts have had profound effects on life. The Chicxulub impact, which struck the Yucatan Peninsula 66 million years ago, is widely believed to have caused the mass extinction that wiped out the dinosaurs. This collision released energy equivalent to billions of atomic bombs, creating a global winter that drastically altered the planet's climate. Despite their destructive potential, impacts also bring life-giving materials. Comets and asteroids are thought to have delivered water and organic compounds to the early Earth, playing a crucial role in the origin of life. These icy visitors from the outer solar system carry the building blocks of life, scattering them across the planets they encounter. Gravitational waves, the aftermath of massive mergers. Collisions between compact objects like black holes and neutron stars produce gravitational waves, ripples in the fabric of space-time. Detected by observatories like LIGO and Virgo, these waves provide a new way to study cosmic collisions. In 2017, the merger of two neutron stars was observed not only through gravitational waves but also across the electromagnetic spectrum, marking the dawn of multi-messenger astronomy. These collisions are also the factories of heavy elements like gold, platinum, and uranium. The neutron-rich environment of a neutron-star merger triggers rapid nuclear reactions, creating elements that are scattered into space and incorporated into future stars and planets. The role of collisions in cosmic evolution. Cosmic collisions are not merely destructive, they are engines of transformation and renewal. From the formation of planets and moons to the creation of new galaxies, these interactions drive the evolution of the universe. They redistribute matter and energy, trigger star formation, and enrich the interstellar medium with the elements necessary for life. Observing and studying these collisions provides valuable insights into the processes that shape the cosmos. Advanced simulations and telescopes, such as the James Webb Space Telescope, are uncovering the intricacies of these events, revealing the forces at play in the universe's grand design. Cosmic collisions remind us that the universe is a dynamic and ever-changing place, where destruction often paves the way for creation. These interactions, whether between galaxies, stars, or planets, are part of the intricate web of processes that define the cosmos. By studying them, we gain a deeper understanding of the universe's history, its present state, and its future possibilities. Pulsars and magnetars, the universe's cosmic lighthouses. Among the most fascinating and extreme objects in the universe are pulsars and magnetars, two types of neutron stars that represent the remnants of massive stellar evolution. These dense, compact objects are the size of a city yet contain more mass than the Sun. Their extraordinary properties make them vital laboratories for studying the nature of matter, energy, and the fundamental forces that govern the cosmos. Neutron stars, the origin of pulsars and magnetars. When a massive star exhausts its nuclear fuel, its core collapses under gravity during a supernova explosion. If the remaining core is between 1.4 and 3 times the mass of the Sun, it forms a neutron star. These stars are composed almost entirely of neutrons, held together by the intense force of gravity. A neutron star is incredibly dense. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. Their gravitational pull is so strong that they warp the surrounding space-time, creating extreme environments that test the limits of our understanding of physics. Pulsars, rotating beacons in the cosmos. Pulsars are a type of neutron star that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky as the pulsar rotates, much like the beam of a lighthouse. To an observer on Earth, this creates a periodic signal pulses of radio waves, visible light, X-rays, or gamma rays, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. This object, initially dubbed LEM-1 for Little Green Men, emitted regular pulses every 1.337 seconds, sparking speculation about extraterrestrial signals. Further observations revealed that pulsars are natural phenomena, the remnants of massive stars. Pulsars are incredibly stable, making them precise clocks. Their regular pulses allow scientists to measure time intervals with remarkable accuracy. This stability has led to groundbreaking discoveries, such as the first indirect detection of gravitational waves through the timing of a binary pulsar system. Pulsars have also been used as natural beacons for navigating spacecraft in deep space. Millisecond pulsars, nature's precision instruments. Millisecond pulsars are a subclass of pulsars that rotate hundreds of times per second. These rapid rotations are thought to result from the transfer of angular momentum in a binary system, where a companion star feeds material onto the pulsar, spinning it up to incredible speeds. The extreme stability of millisecond pulsars has enabled the detection of subtle gravitational waves from the merging of supermassive black holes in distant galaxies. Arrays of millisecond pulsars, known as pulsar timing arrays, act as detectors for these low-frequency ripples in space-time, providing insights into the behavior of black holes and the large-scale structure of the universe. Magnetars, the most magnetic objects in the universe. Magnetars are a rare and highly magnetic type of neutron star. Their magnetic fields, up to 1,000 trillion times stronger than Earth's, are the most intense known in the universe. These fields can distort atoms, disrupt nearby electronics, and influence the behavior of space-time itself. Magnetars emit bursts of X-rays and gamma rays, often triggered by starquakes on their surfaces. These quakes occur when the intense magnetic field stresses the star's crust, releasing vast amounts of energy. In 2004, a burst from the magnetar SCRO 180620 released more energy in a fraction of a second than the Sun emits in 100,000 years. If such a burst occurred within a few light years of Earth, it could strip away the planet's atmosphere. The study of magnetars provides a unique opportunity to explore the behavior of matter under extreme magnetic fields. These environments cannot be replicated on Earth, making magnetars natural laboratories for testing the limits of quantum mechanics and the fundamental forces. Binary neutron star systems, sources of gravitational waves. When two neutron stars orbit each other in a binary system, their immense masses and close proximity create a dynamic gravitational interaction. Over time, they lose energy through the emission of gravitational waves, spiraling closer together until they eventually collide. The merger of neutron stars produces powerful gravitational wave signals, as well as electromagnetic counterparts like gamma-ray bursts and kilonovae. These events are key sources of heavy elements, such as gold and platinum, created through rapid neutron capture processes during the collision. The observation of a neutron star merger in 2017 marked a historic moment in multi-messenger astronomy, combining gravitational wave and light-based observations to study a single event. Pulsars and magnetars as probes of extreme physics. The extreme environments of pulsars and magnetars offer a window into the laws of physics under conditions that cannot be replicated on Earth. For instance, the densities inside neutron stars are so high that matter exists in exotic states, possibly as a quark-gluon plasma or other forms of degenerate matter. Understanding these states could provide insights into the behavior of matter at the smallest scales. The magnetic fields of magnetars challenge our understanding of quantum electrodynamics, QAD, the theory that describes how light and matter interact. In such intense fields, virtual particles can become real, creating effects like vacuum birefringence, where empty space behaves like a prism for light. Pulsars also serve as tools for testing general relativity and alternative theories of gravity. Their precise timing allows scientists to measure tiny changes in their orbits, providing evidence for phenomena like frame dragging, where massive rotating objects twist the fabric of space-time. The future of neutron star research. New telescopes and observatories are poised to revolutionize the study of pulsars and magnetars. Instruments like the Square Kilometre Array, SKA, will dramatically increase the number of known pulsars, improving our understanding of their population and diversity. Space-based observatories, such as NICER, Neutron Star Interior Composition Explorer, are probing the interiors of neutron stars to uncover their mysterious compositions. The detection of gravitational waves from neutron star mergers has opened a new era of discovery, with upcoming detectors like LESA Laser Interferometer Space Antenna, promising to uncover even more signals. These observations will help unravel the mysteries of neutron stars, from their origins to their role in the universe.